Hello. Good afternoon. Am I
Good afternoon,
audible?
sir. Yes, sir, you're audible.
Okay. So I am seeing two raised hand. Yeah, Ganga Prasad.
Good afternoon, sir. Yes, you're audible, sir. Voice is bit low, sir.
Okay. So no, you have raised your hand. So have you anything to ask?
Okay, yes, sir. Yeah, I have raised my hand. Thanks a lot, sir, for responding my query, sir.
Yeah. Okay. How was your quiz?
Quiz was good, sir.
It was good, right? The
Yes, yes, it
questions
was
was
good.
easy.
Honestly speaking, I can say yes, sir.
Okay. Great. How much time it took to solve the questions?
Close to 1 hour, sir.
Okay. Great. Uh, Pritam,
But sir,
you have
conceptually, we
also.
need to discuss a lot, sir.
Yeah.
Solving a problem is one aspect, sir, and understanding the conceptually that is another aspect.
Yeah, I mean, most of the question is quiz was like if you know how to solve it. I mean, if you know the algorithm for solving it, it will be
Right,
easy.
right, 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 sir.
But it is better if you clarify your concepts
Correct,
throughout the
correct, sir.
course. That is
Correct.
better. Yeah. Okay. Yeah, Pritam, you have also raised your hand.
Yes, sir. Sir, I have a few conceptual doubts from activity questions.
Okay, we will come to activity question later. Uh, Before I will summarize what we have done in week 10 and week 11. Okay, then we go to activity question.
Yes, sir. That's a great idea. Yeah, good
Yes,
one.
sir. Yes,
Because
sir.
I think for quiz 2, you have all prepared till week
Week 8.
8.
Week 8, yes, sir.
So, yeah, so I will summarize week 9 and week 10 today.
Yes, sir. Yes, sir. That is very
Although
much
week
important,
10
sir.
deadline is over, but it's better to remember all the things.
So explain the concept of that open wall, sir.
Haha, I will explain definitely.
Yes, sir. Open
That
wall,
will
open.
be more required in week 11 also, the concept of open
We
ball.
have heard that word so many times, but the concept
Yeah,
is still in a
okay,
fluid state.
okay, sure. Yeah, so, yeah, Pritam, how was your quiz?
Good, sir.
It was good. Okay. Others? Uh, Anyone want to share your quiz experience? I mean, is this too easy or moderate? Have anybody find it difficult? Yeah, Dipto.
Sir, I had a doubt from the quiz too.
Okay. What is that?
Should we ask it now?
Yeah, you can ask. I mean, we are just discussing this.
Okay, should I ask now? Okay, okay. So there was in the question there was this function f of x y z from R3 to R3, and
Okay.
in the question it was asking what will be the span for this function to give 0 as the output.
Yeah, right, right.
Okay, so
Yeah.
there was one vector.
Mm-hmm.
That means the kernel of this function is 1. The nullity of this function is 1.
Mm-hmm.
So rank is 2,
Okay.
and this function is neither 1 1 nor on 2.
Okay.
Right?
So
That
what
that's
is
it,
your
right?
doubt?
That's it, right? I'm just checking the
Oh, you are
answer.
asking me whether the answer is right or not.
Yes.
Okay, then I have to open the question.
That's
Yeah,
because
you are correct. Answer key has the same answer.
Oh, okay, then it is correct, no?
I was really afraid to check the answer key, because if the answers are correct, then my exam went well. Otherwise, my exam was a
Okay,
disaster.
okay. But on the, yeah, the questions were easy, I think. So, okay, let me share my screen. Okay, first.
Nothing from affine spaces, sir.
Yes, I was
It
really
will come in
worried.
Ansem. It will come in Ansem. Yeah, can you see my screen?
Yes, sir.
So this was your quiz to paper. Which question were you talking about? This one, last one.
Yes.
Yeah, right. Yeah, so basically you have to find the nullity of this. This is the one of the use of linear transformation. We have created a context around it. So in this question, at first you have to find the null space of this transformation. That
My
is
question was
basically,
a bit different. My question was a bit different. Whether the
maybe in
transformation
set
will be
2. So the numbers may be a little bit different. But this is the gist of it. I mean, you have to find the nullity, you have to find the rank. And as nullity is non-zero, so it cannot be 1 to 1. And as rank is not 3, so it cannot be 1
So just a follow-up question to that, sir.
to 2.
Like with the help of determinant also, we prove that whether the given vectors are linearly dependent or independent, right?
Yeah,
So
right.
for that we write vectors in terms of column of the matrix, right? And if it is not zero, then only it is independent.
But this is only true if suppose n vectors are given in Rn. Otherwise, you
Right.
cannot find the determinant, right?
Correct. No, so I'm coming. Let us say it is 3 by 3, sir. Let us say it is 3 by
Okay.
3.
Okay.
So the moment I put in column, then only I am able to check. My point is that when I put in rows, and I have just checked this, I have done this trial and error, so I get a different answer, sir. I get a different answer.
Uh, it should not be right because determinant of a matrix and its transpose is same, right?
Correct. But okay, so I will check that.
So yeah, so
So,
you
so my
must have made some
so
calculation.
my question was that, sir, is there any thumb rule when to write vectors in terms of column or when to write vectors in terms of rows? Because there are many occasions where we have been told to write vectors in terms of columns, and there are many occasions when we have told to write the vectors in terms of rows.
That depends on what you are doing with those vectors, right?
Okay, like while
So
solving linear equations, we write vectors in terms of rows itself, not vectors
yeah,
like
because you
equation.
have to get back the original system of equation, right?
Correct.
So you have to check whether the multiplication make any sense or not in that aspect.
Okay.
So there you are writing it in terms of row.
So in short, there is
But
no thumb rule. We have to see in what context we are writing, right?
exactly.
Okay. Thank you, sir. Thank you. Thanks for clarification.
Yeah. Okay. Uh, what about this first one? The first one, have you done it, everyone? 3 cross 2 non-zero real matrix, then minimum value of rank. Anyone can give me the reason. I mean, answer is okay, but what is the reason behind it?
We have different sets of questions, sir.
Yes, yes.
Maybe
we
there
have
are two
different-
sets. This is set 1.
Yes, sir. Yes, I had got second set,
First
sir.
one, sir,
Yes, sir. This is not my set.
non-zero.
I'm very much surprised to see the answer, sir. I'm very afraid, sir.
No, this is also not my set. Don't worry. Don't worry. This is also not
There
my
are
set.
two sets. I
There are
think
two
this is
sets.
your
Yes,
set.
yes, sir. This is our set. This is our set.
Yeah. So, yeah. Anyway, so yeah. Tell me. So, what is the reason of the minimum value of rank is
The
1?
matrix is non-zero, so the minimum rank is 1.
Why?
Because if the matrix was 0, then the rank would have been 0. But if the matrix is
But
non-zero, then in that case the minimum rank will be 1 because it cannot be less than 1.
so you are saying for a non-zero real matrix, the rank cannot be 0, right?
Yes, yes.
Why? Can you describe a little?
So rank
In
plus
Because
your
there will
nullity.
be
mind?
at
So
least,
rank plus nullity will be dimension, right? Will be equal to 2 in this case. The number of variables.
Number of columns.
Okay.
Yes, number of
because
columns.
in a non-zero matrix, at least one row will be having
Yeah, 1 will be there.
1. At least one row will be having non-zero element, because of which the rank of that particular matrix will be at least 1.
Okay.
Sir, if we reduce to row echelon form,
Exactly. Right.
at least one has to be non-zero, no, sir?
Yeah, right. That is the answer I was looking for. Because when you are starting to reduce to echelon form, so you have to fix the first row and then doing the row echelon form, right?
So at least I will get one row with.
At least one row will remain non-zero in that case.
Pivot
If
element.
that is also 0, then the matrix will become 0.
Correct.
Right? So yeah, correct. So this was the idea behind it. Yeah. Okay. So let's get back to today's thing.
Sir, in the second question.
Okay.
Okay.
Yeah.
So over here, in the question it is in the condition 3, no wait, condition 2 there are 3 vectors, but in the question there are just 2 vectors, so condition 2 is not possible, right?
No, why? I mean,
All
what are
conditions
you
are
saying?
valid.
This is so you remember the definition of inner product, right?
Yes.
Yes.
So this x1 comma y1 and x2 comma y2, these are two arbitrary vector, right?
Yes.
And I am taking two arbitrary vector, doing the inner product, I am getting this result. Now the inner product will satisfy this condition. So v1 plus v2 is giving is one vector now. v1 plus v2, right? If we add two vector, we will get another vector, right?
Hmm.
So this is the first vector which will sit in the first position, and v3 is the second vector, right? And whatever the inner product we are getting by doing this, the second condition is saying if we do it separately, if we take v1 and v3 and v2 and v3 separately and calculate the inner product, and if we add those two inner product, then we will get back to the same earlier one. That is the second condition.
Oh wait, I messed this up.
Yeah, so here you need your concept to be clear, right? These are the places. Now it is clear what we are saying.
Yes, I just messed up. I thought this the arbitrary thing, it just went off my head.
Yeah.
Sir, can you tell me the weightage of interim exam week wise?
Weightage of what? Each topic.
Yes, no, sir, each week.
Uh, See, basically, again, I am saying the same thing what I have said for quiz 1 or quiz 2. We are, gathering all the concepts of every week and creating a single question like this. So, how can we distribute the weightage like that for weeks? Suppose I am creating a question from tangent plane, and I am tangent plane in week 10, right? Week 10. So that tangent plane also I can associate with some affine space, and then I can go from there to linear transformation. So I cannot really calculate the weightage for each week like this type of question, right? So it's better to go through all the weeks. Okay. So there is no particular weightage distribution for maths 2 that I can say.
Okay, sir.
Okay. But you have seen, no, quiz 1 and quiz 2 are quite easy, right? It is not really difficult.
Yes, the number of questions were very less.
Yeah. So, I mean, number of question is very less means we are giving you some time to think and solve it properly so that you don't do any mistake there.
No, anyways, if we don't know the concept, then we will have a lot of time left, and if we know the concepts even then, we will have a lot of time left.
Yeah.
So less questions means we are putting too many marks on at risk, sir.
That is also true, but if we give more question, then there are two risks.
Like one question was assigned 10 marks, other question said 8 marks. So if something goes wrong, so in that 10 marks will be washed out.
But you are getting the time, right?
Yes.
So if the number of question increases, then there will be again a problem like this. So you have to attempt many questions to get marks.
Yes, sir.
That is also an issue.
Less number of questions better.
So in end term, I think there will be more number of questions. Definitely, because
so more number of questions will always be a problem, sir, because we have to think
in
an
end
answer.
terms, actually, I am saying it is 100-mark paper, right?
So, but sir, every question is that.
So again, it will be 50 marks, I think.
So the trend I am seeing is that a lot of there's not a straight away answer. We have to think a lot, concepts involved. So I think number of questions less means we will have a time to think. Otherwise, it will be difficult, sir.
Yeah. But in end term, what I can assure you, there will be, a lot of questions which will check your concept. Okay.
Yes, sir. That's why, sir. That's precisely why we need to have less number of questions, not more. The concepts are conceptual understanding tested.
Oh. Yeah. So let's start with this. So in week 9, we have started with this multivariable function, right? So before going to multivariable, can someone tell me what was the definition of function in one variable? You have seen it in maths 1, right? What is the
Okay.
function?
Sir, it is a special kind of relation, sir. Like there are two sets, set A and set B. So each element of set A must have a unique image in set B. So
Yeah.
it's a special kind of relation, kind of thing. That's my understanding, sir.
Right, right. Anyone else? Anything he has missed? So suppose, let me do it here itself. Suppose I have two set, what he has said, A and B. Okay. So suppose there are four elements like this, and there are suppose three elements like this. And I am defining A is going to here, this point is going to here, and this point is going to here. Is this a function?
No, sir. We are
Why?
missing out the fourth element. Na?
All points of A
I
must
said
have
each
a
element, sir. I
relation
said
with
each element of set A,
Exactly.
each element of
Exactly.
set A must have a unique image in set B.
Exactly. Right.
Yes.
So if I send this to this one, now is this a
Now it's
function?
a function. Yes, sir. Now it's a
Yes.
function.
Okay. Now if I draw this also, is this a function?
No, no, because it
Why?
is not unique. It
Hmm.
is not unique image.
Exactly. So one element cannot go to two different elements, right?
Yes, yes.
Yeah, great. So you remember the definition of function. So the definition for multivariable, this portion remains same.
Sir,
But
here I have a conceptual doubt, sir.
hmm,
Like in terms of set, I am very much clear with the definition, sir. But when
hmm,
we write in terms of y and x, na, sir, then I get confused. Like when we say, say
okay.
for example, 2x plus 3y equal to 10. Say for example, let us take an equation, 2x plus 3y equal to 10,
That
right?
is equation, right?
But
That
when
is
if there are two variables x and y, and the
hmm,
moment we convert it into function form like y equal to that we modify, then we say it's a one variable calculus, one variable function. So that
right.
creates confusion in me.
Right. So okay. So let's start from here itself. Suppose we have this equation.
For 10 you can write for simplicity.
Huh?
Yes, 10. For simplicity we can write 10. Yes.
Okay.
Yes.
So that's okay. Yeah. So I can write it like this, right? Okay. So I can take everything on the other side and write y like this. So what happens here? If I give any value for x, I will get a defined value for y, right?
Correct.
So I can treat this as function of x, right?
So there are two variables, na, x and y.
But here this y is dependent variable, right? Y is dependent on x, correct?
So does it mean that we should not talk about dependent variable? We should focus only on independent variable.
I mean, you can write it again like this. So x equal to 10 minus 2y by 3.
Yes, sir.
This is
Yes.
also a function, but this is a function of y, the other variable, right? So according to our conveniences, we can choose the dependent variable or independent variable. That is in our hand.
So we
What
bother about
function we are trying
independent
to do.
variable. So we bother about independent variable, not about dependent variable, right?
Yeah, right. Right.
Because here,
But that choice is in our hand. That is my point.
choice is in our hand. Because
Right.
here, yes, in case of first one, the input variable becomes x. It means set A goes to x and the set B that goes to y. Output goes to y, right?
I mean, forget all this.
Okay.
For the first one,
Yes.
this one, for defined value of x, you are getting defined value of y. And now y is in our hand. So you are giving the input in x. So we are getting output as y. So our input is this variable is our independent variable in that case. So we are taking function of x. But in the second case, you are giving input in y and getting output as x. So when I am writing this, I will write it as function of y.
So it
Okay.
is we are bothering about independent variables, not dependent
Exactly.
variable.
Exactly. Okay.
Okay, sir. Okay.
Okay. Great. So till this point it is okay. Now for multivariable, what we are doing? Okay. And another thing, let me ask: what is the graph of a function? That is also discussed in calculus. But what is the graph of a function? Anyone remember what is the graph of a function?
Plotting of y variable against x variable.
What does that
I
mean?
mean, that is independent variable versus dependent variable.
Huh. So basically, suppose I have function of x. So I am taking this, right? X comma x f of x, right? All set of all, I mean, set of all points like this, right? So this was the definition of graph, right? Where x is in our domain, correct? So we are taking all the inputs as x and on the output and taking consider this as the point. So along this direction, I am writing x. Along this direction, I am writing f of x. Okay, the outputs. So whatever we get, that is that is the graph of our function. Is this okay?
Yes, sir.
Yes, sir.
Okay. So if I draw this one, if I draw this one, is this a function?
No, sir.
Why?
It fails that definition that each element, one element cannot have two
Exactly.
outputs. So
It
Yes,
is
If
sir.
I
not
draw
passing the vertical line test.
correct. The
Yes,
technical
sir.
and vertical line test.
Exactly.
Yes.
If we draw a vertical line, it will intersect more
Yes.
than one point, so it cannot be a function.
And
Yeah.
the basic is that one input is giving two output.
Exactly. More than one output.
Yes,
Yeah.
more than one output, sir. Yes.
Yeah. So okay. Now in this case, for multivariable function, what is the case? So instead
কিন্তু
of
খিদে পেয়ে গেলে এরকম
now,
করবে,
now
খিদে
what
পেয়ে
about
খালি বিকেল বেলায় খিদে।
Who is talking, sir?
okay? So in multivariable function, we are choosing our domain. Instead of R, we can choose R2, R3 and all this. Okay. So we are choosing our domain inside Rn, where n is strictly greater than 1. So basically what we are doing, suppose I am taking this function from R2 to R. So our output is inside R, that is a scalar, and here we have two variables. So if of x, y, suppose I am, so here it is x, but let's take x plus y. So here our domain is inside R2. Basically here our domain is R2 itself. And we are getting an output as a scalar, okay, as a single value. So this is the concept of multivariable calculus. So this is called scalar value multivariable functions. Okay. So some examples here are given. One is f of x comma y equal to x. So in this function, it is independent of y. Whatever the value of y you are taking as input, it does not matter because it is only giving out the output as x. And suppose we can take f of r, f from R3 to R, and we can consider like this. This is also a function. And so here what we are doing, we are taking S1. What is S1? S1 is basically a subset of R2 where x square plus y square is 1. That is our S1. Basically the circle. So we are taking all the points on the circle. This one, all these points. Okay. And I am giving my output as x square plus y square. So basically the concept is we are taking some domain inside R2. So there are two variables and I am getting an output in R. Okay. So how it will look like?
So, but whether that circle will form a graph, sir?
No, circle is our domain. So let me show you what actually I am talking about. So suppose I am taking this. This is my domain in R2. So I am taking all these points from R2 and I am getting an output in R. So this is my real line R. So this is how the function will look like.
Okay.
Okay.
So there are two independent variables here.
Exactly. So we are giving choices for x and y. I am getting some output depending on x and y. Okay. So our domain will also will be inside R2 or in general it can be inside Rn. Okay, and we are getting output as a scalar value. Yeah.
Sir, you have written previously that x square plus y square is equal to 1. So how can they
This
both are
is
independent?
not exactly this picture. So yeah. So for this one, S1 is, so let me use a page. What is S1? S1 is set of all point xy such that x square plus y square equal to 1. So what is this in R2? This is a circle, right?
Yes, sir.
So I am taking all those points which are on this circle and I am getting an output on real number. This is my real number line. I am getting some output. So I am considering my domain to be only those points which are on this circle.
The output is one, na, sir, for this function.
So
Output is one.
basically in this function, what it is mentioned here, S1 to R, xy is going to x square plus y square, right? This was given. Now, as all the points on this circle are basically x square plus y square equal to 1, so this is basically a constant function.
Yes.
Okay, is this clear?
Yes.
Okay, great. But instead of x square plus y square, if I take, suppose, xy, right? Then we will get different values, right?
Yes.
So we are taking all those points for which x square plus y square equal to 1, and we are getting different values. So suppose I am taking which 1 comma 0 is on the circle, right? 1 comma 0. So what is f of 1 comma 0? It is 0.
0.
No, 1 into
So
0. If I taking f of x y equal to x into y, so it is 1 into 0. Now, can you tell me, is this function, I mean, what are the other values for which this will give 0? What are the
Any
other numbers?
coordinate is 0.
Both are
0, 0, 1, 0, 0, 1.
-1, 0.
Exactly. There are 4, right?
X 0, Y 0, Y, and 0, 0.
So, no, still, I mean, we can solve those, right? When x is 0, what is y? Y square equal to 1, that means y can be plus minus 1. And similarly, if y is 0, then x can be plus minus 1. So there are 4 points only, right? These two and this two, right?
So you're talking about x square plus y square or x y square? Which one?
So I am talking about this function. This is my domain and this is my function. F of xy equal to x into y. And I have asked that what are the points which are going to 0. So basically, these 4 points are going to 0. This one.
Yeah, for xy it is different. xy is different. For f of xy, which is a second equation, that is a totally
This is the function we are considering. This is the function.
Yes, sir, but that is not related to the circle at all. That we can have.
No, this need not be a circle. My domain is a circle. I am taking all these points from this circle.
For xy.
But sir, in that case, there is no necessity now that it should be always be 1 0. It can be 2 0 as well, now, because
Yes,
it's
sir.
f(x).
But is 2 0 on this S1? Is 2 0 in S1?
S1 is always that coordinate, one of the coordinates to be 1 over.
So I am taking my domain to be S1.
Okay.
This is my domain.
So what I was saying is when I'm taking xy, f of xy is xy. So this is a multivariable scalar value, right? So I can have in either of them should be 0 for me to get a 0, right?
Right.
So which means I can have, let's say x is any value, but y is 0.
But that's what I am saying. Suppose you are taking 2 comma 0, right?
Yes.
Then also it is going to 0. But my point is here I have mentioned a domain. Is 2 comma 0 inside my domain?
No.
No, right?
Why, sir?
What is my domain? Domain is S1. And what is S1? S1 is all the points in the circle.
Okay, you're taking the domain from.
I am defining a domain. I am not taking whole R2.
Oh, okay. You are taking from this x square plus y square one.
Exactly. I am taking this S1
Okay.
as my domain.
Okay.
If I take a domain to be whole R2, then whatever you are saying is correct.
Okay. Correct. Thank you.
But my for this example, my motivation was I can choose a domain inside R2.
Okay.
Right? There may be some cases where domain may not be whole R2.
Yes.
Right? So when you have learned single variable function, there may be some points where all the domain may not be whole R, right? There was some example, right? Suppose fx equal to 1 by x. What was the domain?
R minus 0.
R minus 0, right? You are eliminating 1 point from R, right?
Yes, sir.
So it was a subset of R. Similarly, in this case also, there can be cases where we can choose domain which is not whole R2. That was my point. Okay? Is this clear?
Yes, sir.
Yes, sir.
Yeah. Okay. Okay, great. So we have understood what scalar valued multivariable function really look like, and there is another type of function which is vector valued multivariable function. Now, what is this vector valued multivariable function? It is basically, again, my domain is inside Rn, but here I am getting the image on Rm where m is greater than 1. I mean, I am not getting any single scalar. I am getting a vector, right? Vector which is in R2 or above. Okay. So suppose this function f of xy is going to f of xy. This is a identity function, as you know. So here it is from R2 to R2. So I am getting my output as a vector, as a tuple in R2. Okay. So this type of cases should not be there. This is in R. We are getting the output in R. So it is not a vector value function. It is a scalar value function. Okay. Is this clear? So
Yes,
suppose I am taking f from R3 to R2, f of x, y, z equal to x square plus y square and y square plus z square. This is a vector value function, right?
Yeah.
Yes, sir.
Because we are getting my
yes.
output in R2.
Okay.
So suppose I am taking 1, 0, 1. What will be my output? This is 1, this is 1. Right?
1, 1.
Yes.
So basically what I am taking 1, 0, 1. So suppose this is x, this is y, this is z. So 1, 0, 1 here on this xz plane. This is my point, and I am getting my output in xy plane. This is x, this is y. So 1, comma 1. So 1, comma 1. So basically I am getting like this.
So in the same graph, how to plot?
Which one?
In the same graph, like in case of single variable calculus, we used to take
No, it is difficult to plot in same graph. No,
But it will be on the xy plane.
that is the point. Because over,
Sir,
how can you plot?
this mapping is clear, sir. What mapping you are showing now, that is clear. Like 101 is mapped with 11, right? Yes,
Right.
that mapping is clear. I'm just
But
thinking
inside a same graph you cannot put, because if you want to put this in same graph, you have to visualize R5.
Correct.
Right? So it is difficult.
Or we can say
You cannot draw it basically.
We can say that from xz plane to xy plane, right?
So whatever till which point we can draw, that is basically we will learn in this course. R2 to R. We can plot this type of function, because then we can draw this whole thing inside our R3.
What about
XY.
R2, R2? What about R2, R2, sir? R2, R2?
Then also it is, we can draw, but it is again difficult to visualize. We can draw it, because at that point, okay, let me finish this, then I am coming. So suppose I am drawing this. So what you are getting basically. So let's go to GeoGebra. Okay. You can see my screen, right?
Yes, sir.
It's basically to a square, to a circle, right? From a xy plane to a circle.
Okay, let's see what So f of xy is going to x square plus y square. Yeah. Can you see it?
Yes, sir.
So basically, this xy plane, which we are taking, that is our domain, right? And we are plotting the output along z-axis, correct?
Yes, sir.
We are plotting the outputs along z-axis. So basically, we are getting a surface. For each point, we are getting some point. Are you asking anything? I have missed. Anybody is asking some question? No.
No, sir, continue.
So basically, we are getting taking some point on this xy plane, and we are plotting it along z-axis. So we'll get a surface. So suppose 1 comma 0. Okay, f of 1 comma 0. What is f of 1 comma 0? We are getting 1. So I am considering a point. So let me see what is the point. So 1 comma 0 is going to 1. So this is my point. 1 comma 0 comma 1. Correct? So you can see this point is on this here at this position. Okay?
So
You can
this
see
is
it.
R2 to R. This is R2 to R, right?
Yeah, this is R2 to R. Okay? So this is the 1 comma 0 comma 1. You can see. Right?
So whether vertical line test is applicable for multivariable also?
Yeah.
Vertical line test is applicable for multivariable also?
Yeah, but here you should remember that this is the output we are seeing. Right? This is the surface which is output we are seeing here.
I know, but theoretically it is applicable, right? Theoretically, concept.
Yeah, so we are not getting for a single point, we are not getting two different output. 1 comma 0 is only going to 1. Right? Correct, no?
Yes, sir. Yes.
Yeah, so that is okay. Okay, so have you got the idea how we can plot this out? Okay. Now, if we consider R from R to R2, then also we can see like this, but we have to then choose where my R is. I mean, which axis should I choose as R, and which plane should I choose as my R2. So that choice we have to make. Okay. But we are really concerned about this type of situation where we are taking map from R2 to R, because that will generally give a surface, and we are basically trying to visualize how a surface behaves. Okay, am I clear?
Yes, sir.
Okay, so can you tell me, I mean, why this function is not going below z-axis? I mean, below this xy plane?
Square term, sir. Square.
This is sum of two square terms, so it is always positive, right?
Correct.
So it will give always positive z values.
Yes.
So it will always be over xy plane, not go below that. Okay, great. So let's see another example. Xy. So this is my xy. Okay. 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 So this is my xy. So if we let's go back to this one, and then I will again come to this. So x square plus y square, which I have drawn earlier. Let me go back to that one. Okay. Now, if I draw a plane, suppose I am drawing a plane z equal to 3. Okay. You can see the plane is cutting this surface, right?
Yes.
And what is the solution of that? That will give me a circle, right? And can you tell me what is the equation of that circle?
X square plus y square equal to 3.
Exactly, x square plus y square equal to 3, because we are fixing the z equal to 3 value, right? So all this point which is on this circle is basically giving me x square plus y square equal to 3. Okay, the x coordinate and y coordinate will give me 3 by squaring them up and adding those. Okay, so if I change this plane, suppose z equal to, I am writing 5. So yeah, so this is x square plus y square equal to 5. Okay, this is the circle we are talking about. Okay, so if we change the value of z and draw a different plane, it will cut those cut that surface and it will generate a circle. Okay, is it clear?
So, sir, I just want to in GeoGebra, how to select the options, sir? Because I just checked up with the website, so a lot of options are there. Which one
This
to
is GeoGebra
choose?
3D.
3D.
GeoGebra 3D.
So,
Then
do we need to click on that algebra something there? Left side icon, no? There are two ones. Some tools
you
are.
have to click on algebra. Yeah.
Okay. Thank you.
Okay. So yeah, you can plot different type of function here and you can check it. Okay. So this is how it look like. Now, what about when I am talking about xy, the function which I have written this one. Now, if you take z equal to say 1, what I will get? It will again see two different hyperbola will generate, right? xy equal to 1, that is the hyperbola, right? Equation of the hyperbola. Y equal to 1 by x. Correct? Is this okay? If I plot z equal to 1, so that will give me a plane and it will intersect this function and it will generate xy equal to 1, right? That is y equal to 1 by x, this two plot, right? These two curves will generate. Okay, is it clear? Can you visualize it?
Yes, sir.
So yeah, so before going to tangent plane and all this higher stuff, first we have to visualize what multivariable function look like and how they behave. This is really important. Okay.
So it means here xy has become y, right? Because sorry, z is equal to 1, is it?
So here basically on all those points on this curve is basically xy equal to 1.
Xy equal to 1 of
1. Okay. So you can see two curves, right? Here it is one curve, here it is another curve. So these two curves will basically give you xy equal to 1 function. Okay. Is it clear?
Yes, sir.
Okay.
Yes, sir, very good.
So I suggest you to go to GeoGebra and take some example and check how this function look like. So in 2D, you know how sine function look like, right? Sine curve, sine x.
Yes.
That you know, right?
Periodic.
Periodic. But what it looks like here? Just sine x I am taking. Okay. So can you see how it looks like? It will give me a surface like this. Okay, it is also periodic, but this is surface periodic. Okay, the surface is taking this periodicity. Okay, because it will distribute throughout y. Okay, is it clear? So I am just taking here, I am just varying my value of x, and for different y I will get different position over this xy plane. That's why this surface is generating. Is it clear?
But in
So
output
if
we are
I
taking, so in output we are taking only sin x, right?
in output we are taking only sin x.
So input we are giving from domain, we are passing a value of x and y, right?
Right.
And then we are considering only the value of x. We are ignoring the value of y, right?
Right. Exactly. Okay. That's why this surface type of thing is coming. Okay. So suppose I am taking z equal to no. So let's first take y equal to 0. What I will get. So I am taking y equal to 0. That means this is my, which plane is it? Y equal to 0?
XY plane.
It is no, xz plane.
Exactly.
Xz plane, right? Y equal to 0. So it is my xz plane. So when I see in the intersection, you will get one sine curve. Can you see? This is the curve you are getting. Right? You will get one sine curve. Correct? On xz plane. Is it clear? Can you visualize this? The plane is intersecting this surface and giving us one sine curve on xz plane. Right? Okay.
Bisecting the curves.
Can we remove the curves to see the? Can we remove the curves to see the curve that is formed?
Okay. 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 So let me remove this one. No, this one I cannot remove. So what I can do, I can take intersect. Intersect if now the curve is bold. Can you see that curve now?
Yes.
Yeah, so that is the curve we are getting. Is it
What is
clear?
the function you use, sir, for this?
Intersect path.
Inside the set path.
Intersect.
Okay.
Intersect of f and g. Whatever the
Okay.
curve is giving, that is the our sine curve on this
Okay.
xz plane. Is it clear?
Yes.
Once more.
Once more. Okay. So let me start with here. So first I am saying fxy equal to sine x. So this is the function, right? This is the graph of this function. We are plotting it. We are getting this surface.
Sir,
Now I am
output will be sir here output will be in the z plane, right? It means like z equal to sine x, kind of you are saying, right?
exactly. This is the z equal to sine x surface. Exactly.
Okay.
Okay. Okay. Now I am taking a plane y equal to 0. That is my xz plane. So this is my xz plane. Okay. This is the xz plane we are talking about. Now this sin x, z equal to sin x surface and this surface y equal to 0. These two surfaces will intersect. And what is the curve we are getting after intersection? This is the curve we are getting. Okay. This is exactly the sine curve. Right. Now I can remove this. You are seeing this is the sine curve we are getting. This is the intersection of those two curves. Is it clear? Now is it clear, no?
Yes, sir.
The sine curve we are getting? Okay, great.
Sir,
If we take this one, yeah, what?
yes, sir.
Someone has asked.
Yes, sir. So in the lectures, sir has used a lot of graphics and many visuals to explain things, and these were very complex to do it on our own. So I think a tutorial on GeoGebra would have helped.
Okay. Okay, today I am saying some portion of it, and
Yes, sir.
in next
For
session also
example,
I will
yes,
give some.
the intersect part is a new thing that we came to learn today.
Yeah, right.
Without these,
Yeah,
we can't
so
plot those and visualize ourselves while we are doing the lecture.
so I am trying to give you that today. Okay, what to
Okay,
what
sir.
extent it is possible. Okay.
Sir, if
How
possible,
we can
please.
access these different functions? Is there a function library in this GeoGebra from which we can access
Function
these
you can
functions?
type by yourself, no?
Okay, but we
Whatever
need to
function you will
know the
give, it
name
will
and
give you a graph.
okay, okay.
Okay, whatever
So, but
function you
there
will
must
type,
be
it
some
will give you a
specific.
graph.
Sir,
Yeah.
sir, sir.
1 minute,
Sir,
1 minute. What?
Sir, do we have any tutorial for this?
No, till now there is no tutorial for this, but there are many videos in YouTube you can go through. That is
Actually, I've
also
had,
there.
actually I had asked this on Discourse also.
Okay.
But problem is when I try to enter some formula, I don't get to this page. So if you could share the URL, it would be very helpful.
Okay, so after today's session, I will share all the URLs. Okay.
Okay, sir.
And I have also myself made some visualization, as you can see here.
That would be wonderful, sir.
So I will share all these. Okay.
Thank you.
This type of visualization I have made. So I can share it with you. Okay. This is on visualization for partial derivative.
So, sir, for example, like here, intersect path derivative, these are the functions available, right? So, but we may not recall all those things. Will it work auto assist kind of thing like we have in some Python?
Yeah, so when I am typing intersection, it will suggest me this.
Okay. But is there, like, if you want to see like pressing control space or something like that, some option there to get the list? Because maybe like as of now we recall only intersect and derivative, but there will be other things.
Okay, so I will give you some this type of link in what I have just now shown, and those will be enough for this math to.
Okay.
So is that okay? So I will give you this derivative is a function like this. All this.
Sure.
Yeah, okay.
Thank you.
So here also I have made some card. Okay, so I will anyway.
Sir, one question, sir.
Yeah.
Sir, is there any option it will display all the local maximum, minimum, and saddle points?
Yeah, there is an option for critical points.
Okay.
So when I will come to critical point, I will show you. Okay. So yeah, now what I have done here, I have changed the plane y equal to 4 instead of y equal to 0. I have taken y equal to 4. So as you can see, this car will shift at this position. Correct? The intersection car. Okay. So till this is clear, right? This function is clear. Okay.
Yes, sir.
Okay, great. So we can identify and visualize a little bit about this multivariable function, mainly scalar value multivariable function.
Sir, just drawing a parallel with single variable calculus, sir. So whether the types of functions which we had studied, like injective, surjective, and bijective, so those are also equally applicable for multiple variable, both scalar and vector valued multivariable functions.
You can define it, but for multivariable, we are not really interested on one-to-one or one-to-one. Because for that, we are interested in those cases which are linear function, because that will give us linear transformation, and then we can check whether it is an isomorphism or monomorphism.
In linear transformation, that surjective becomes isomorphism, right? Sorry, bijective.
Bijective isomorphism, exactly. So until that portion, we are interested.
But conceptually, it is there. Conceptually,
it is obviously there. It is obviously there. Even in higher, if we study mathematics, there was a subject called topology. So there it is really needed. Not only injectivity and subjectivity, but along with that, continuity of the function is also there. Continuity and differentiability, all this comes in the picture, and there we discuss whether two surfaces are kind of same geometrically or not, have the same geometry or not. That property we study there. Okay, so I am not going to the details. That is really hardcore mathematics going on there.
Okay, sir.
So yeah, definitely the concept are there.
Okay, sir.
Okay.
Okay, sir. Thank you.
Okay, great. Now, after that, what we have seen, we have seen the partial derivative of a multivariable function. So, can someone tell me what is the partial derivative of multivariable function? I mean, what does it suggest?
How the function is varying with respect to a particular axis.
Exactly. How the function varies with respect to a particular axis. That means respect to a particular variable, right? So multivariable means we are dealing with more than one variable, as I have already mentioned. Now for each variable, suppose I am fixing one single variable, say x2, and I want to know how the function behaves with respect to x2, how the functional value is changing with respect to x2. So what I will do, along that x2, I will increase the function a little bit. Along the neighborhood, I will check the function, behavior of the function. Okay. So in single variable, what we have done? So f is from R to R for single variable function. X is going to f of x. And what we have done here, we have defined limit h tending to 0, f of x plus h minus fx by h. So what we are doing here, if you remember this, suppose we have a function like this, graph like this. So at this point, suppose this is my x equal to a. So what we are doing, we are taking a plus h. This is a plus h. So I am incrementing the h thing along the x-axis, and I am seeing what is the difference of the values, right? So this is my f of a. This was my f of a plus h, right? So, and I am taking now, what is the increment? Increment is f of a plus h minus fa. This is a defined between these 2 points, the value, functional value, and by h, right? So this is the increment in this small neighborhood, and I am making this h as small as possible. So I am coming near to this value a, x equal to a, right? So what was this? This was my f dash. If this limit exists, then we call it the derivative of the function at x equal to a, correct? Now same thing we are doing for multivariable function. So now we have more than one variable. Now suppose we are fixing one single variable x2. Now we are doing exactly the same thing. You can see there is a similarity between these two definitions, correct? This definition and this definition. There is a similarity between that, right?
This is partial derivative.
So what is EI, sir, here?
So I am coming to what is EI. EI is basically which variable we are considering, the unit vector along that. You know standard vectors, right? E1, E2, EN.
Yeah, except
Right?
EA,
One
all the other
coordinate
will
1
be
and
0
others are
and DA
0.
will be 1.
Exactly. Now suppose I am, so let's visualize in case of
But sir, here
two
this
variables.
limit is for partial derivative, right?
Yeah. Yeah, here we call it partial derivative because we are considering it for only one variable. I mean, we are not considering we are considering it partially. That is the idea behind it. Okay, we are not considering about the total derivative. There is some concept of total derivative, which is in week 11. Okay, we will see that what is total derivative. But here we are considering only for a particular variable in this case. Okay, suppose I have a function from R2 to R. Okay, so let visualize for small function. So my function is x comma y is going to f of x comma y. So suppose that with respect to x, I am trying to see what this is, right? So what I will do, I will take an increment along x-axis only. Okay, y is remaining fixed. Okay, so this is my increment, and what is this? This is h, correct? Is this clear? Can we now match it with this definition? Yes, we can. Now here, if we consider it as a vector, this x is basically our x comma y, right? So instead of x comma y, let me write it x1 comma x2.
Sir, this h is not clear because in case of single variable, what used to happen? We used to do a plus h minus a, right? So we used to get h. Like in case of single variable, sir, we used to do a plus in the denominator. We used to write a plus h minus a, right? So a cancels
No,
out.
that is not minus h. This is, I mean, that is true, but where this h is coming from? H is coming from this increment in h.
That's
in x-axis, right?
a plus h, a plus h minus a, so we are getting h because we are subtracting a plus h and minus a, so we are getting h. So how
because there is only one axis we are considering, right?
Correct. So
here what we are doing, see, these two variables we are considering, our function is along this z, right? So we are getting something like this function. This is my surface, okay? Some surface like this, okay? I am only considering along x-axis, okay? So here I have a, here I have a plus h.
Okay.
This is my f of a comma y, okay, along here. So this is not a single, so everything y means this whole line, right? And what is a of a plus h? This is again a single curve like this. We are getting two different curves. Now what is the difference between this along x-axis? What is the difference? This is h only, right? That is what we are doing.
Okay, so the same definition.
Is it clear? Or should I draw it more?
No, fine.
Clear?
Thank you.
I have missed it here. Okay. Let me draw it more clearly. So this is z-axis. Like this, okay? Some function. So a, what is f of a comma y? F of a comma y is this curve, right? Okay, some curve like this. Similarly, f of a plus h is some curve like this, right? For different y, we will getting different point, correct?
Yes.
So like this. Can you visualize it? Now for a plus h, we are also getting different point like this. So we are getting two different curves. Now I am making this a plus h closer to a along x-axis. So the difference is basically a plus h minus h along x-axis, right?
Minus a,
and
sir.
we are
Minus
seeing
a.
how it approaches. Clear,
So,
right?
so minus a plus h minus a.
Minus a, correct. Okay. So basically, if we consider a vector along this x-axis, there the unit vector is coming in the picture. Along this vector, how the function changes. Okay. Is it clear?
Yes, sir.
Okay. So what I was doing, I was basically now considering x1, x2. So this is f of x1 comma x2. Instead of xy, I am writing this so that I can write it in terms of vector. Okay. So this is my x. Now what is I am considering along this unit vector along x-axis. So my e1, what is e1? This is 1 comma 0. Okay. Now if I take this, h is a scalar, right? So this is scalar multiplication of a vector, and then I am adding it. So this is x1 comma x2 plus h into 1 comma 0. What I am getting? This you can tell, right?
Yes.
x1 plus h comma x2, right? So this is the first thing we are getting. So this is f of x prime, sorry, x vector minus f of x vector, and comma y is there because we are fixing y. Okay.
So sir, I have a basic question. Suppose here you assume that it is 1 0. If I assume that it is 1 1, then what will
we
be
can
the...
do that, but that is not along any particular axis. We will come to that. That is basically called directional derivative.
No. So I am saying, yes, I agree with you, but here I am saying, okay, that suppose this definition of x, y, z is a standard definition. But if I rotate these things, okay, this axis I rotate, this axis x, y, z axis I rotate. Okay, then this 1 0 will not be 1 0. No, there will be some value will come.
Exactly.
Then this will not be x1 plus h, x1 plus some fraction h plus x2 plus. Maybe I am doing something wrong.
No, I am not getting a question.
Oh, so maybe I am confusing myself.
You just think and phrase it and then answer. Okay.
Okay.
Okay, so basically what we are getting, so here I am getting x1 plus h comma x2 minus f of x1 comma x2, right? This is the increment. I mean, this is the change in the functional value. Now, what is the increment? I am dividing it with h, right? So this is the derivation which we are taking as a partial derivative with respect to x1. Okay, with respect to x, I can say at the point x1 comma x2. Okay, is it clear? Similarly, we can do it for y-axis, because for y-axis instead of 1 0 I will take 0 comma 1 vector. Okay, now you can generalize it in terms of Rn. So for Rn we are getting ei. Whatever, if I considering it with respect to xi, I should consider my vector to be ei. Is it clear? The definition of partial derivative and the concept of partial derivative is clear.
Yes, sir.
Okay. Do you have any doubt, anyone?
At that point, we are taking 1 0 or 0 1 because we are making one axis constant, one variable constant, right?
Exactly. Exactly.
Like I am taking
So
1 0.
Along that axis, what is the unit vector? That is our question. Along x-axis, what is the unit vector?
I am taking 1 0 since I am keeping y constant here, right? And I take 0.
Don't remember it like that, because conceptually what we are doing? Conceptually we are doing is along x-axis we are taking the unit vector, and along that unit vector what is the change of the function? That is what we are doing. Okay. Now along x-axis what is the unit vector? Unit vector is 1 comma 0, right? If we are in R2, in R3 it is 1 comma 0 comma 0, right? And so on. Now if we consider along y-axis, what is the unit vector? It is 0 comma 1.
0 1.
0, yeah. 1, yes. So other variables are constant.
So along that unit vector, what is the change? Because that will be, I mean, this concept will be generalized in terms of directional derivative. There we must have to remember the unit vector along that direction. That's why it's better to start conceptualizing this in terms of partial derivative. Okay. So partial derivative is because is basically we are taking fixing some axis, and we are taking the unit vector along that axis and trying to visualize how the function changes along that direction. Okay. So is it clear what partial derivative does?
Yes, sir.
Okay, great. Okay. So yeah. So let's solve this problem. So I have taken a function which is domain inside R2. So this is a function from a subset of R2 to R. So scalar valued function of two variable. Now what is the partial derivative of f with respect to x at the point 0 comma 0? So with respect to x means we are considering along x-axis, right? So what we should do? 0 plus h comma 0 minus f of 0 comma 0 by h, right? We have to check whether this limit exists or not. If this limit exists, then that is the partial derivative of f with respect to x at the point 0 comma 0. Is this clear? Is this clear?
Yes, sir.
Okay. Now what is f of h comma 0? Now function is defined like this, okay? So at 0 comma 0 at origin it is 0, and other that origin it is defined as x square y by x cube plus y cube. So h comma 0, when h is tending to 0, we are considering that h is not exactly equal to 0, right? So this h comma 0 is not exactly 0 comma 0. So we will take the definition when at least one coordinate is not 0, right? So what is f of h comma 0? F of h comma 0 is h square into 0 by h cube plus 0 cube. So it is again 0, right? So limit h tending to 0, this is 0 minus what is f of 0 comma 0? 0 by h. Now what is this function? The above term is always 0. So anyway the function is going to 0. Is it clear? So the partial derivative of f with respect to x at the point 0 comma 0 is 0. Okay? Is it clear?
Yes, sir.
Okay. Now, okay, this one. Okay, before going to this one, let me give you another function. So, can you tell me at the point 0, comma 0, what is the partial derivative of this? Same question along x-axis. At the point 0, comma 0. So,
It's
what
0.
we should
Will it be 0 again, sir? 0.
So let's see what it comes. Okay. So again, I have to do this same thing. So what is f of h comma 0 now?
So 0.
F of h comma 0 is 0?
No, 0
Is
then
it?
0 then 1 plus
H comma 0. So mod h
yes
into 1 plus 0, that is mod h, right? Minus f of 0 comma 0 is 0, that is correct. This. So what I am getting, limit h tending to 0, mod h by h. Now what is this limit?
1.
Is it?
So plus or minus 1, no?
So what does it mean if it is plus and minus 1?
Not a unique
It's
limit.
not,
Limit does
yeah,
not
it's not a
exist,
unique
right?
limit.
Exactly. So limit does not exist.
Maybe it doesn't
right?
exist, yeah.
This is the mod function, no? So you remember that mod function is not differentiable at 0, right? In single variable calculus. You remember that, right? This is the same thing. Okay, in single variable calculus, when we are doing, so let me recall it. R to R, okay, f of x equal to mod x. Is this function differentiable at 0?
No.
No, sir. No.
No. How we have proved that?
Because it have the sharp point at the short
Exactly.
turn.
So if
At
we
origin will
draw
be
this,
sharp bend. Yeah.
sharp
Just
bend.
like V.
This
Yeah.
is the graph of the function, right? Mod x. So this is basically fx equal to x when x is positive or equal to 0, minus x when x is negative, correct? Correct? That's also the definition, right?
Right. Sir.
So when I am approaching from the right side, f of 0 plus h, I mean f of h minus f of 0 by h. So limit h tending to 0. Now h is from positive side, so I am taking h by h. This is 1. So when I am approaching from the right side, the slope is 1, right? This is tan 45 degree. Now when I am approaching from the left side, slope is minus 1, right?
Yeah.
So limit h tending to 0 minus f of h by h. This is minus h by h. Limit h tending to 0. This is minus 1, right? So when I am approaching from the right side, I am getting 1. When I am approaching from the left side, I am getting slope to be minus 1. So that is not unique. That's why it has a sharp turn at the origin. So it is not differentiable. So it is exactly the same thing happening here.
Sir, just one doubt here, sir. The limit is not defined. That point is clear, sir. But my point is that whether it is not defined because of mod function or it is because of sharp edge, or there is any relation between mod and
Mod function is one example. It has a sharp edge. That's why sharp edge means what? Sharp edge means at that point when we are approaching from the right side and approaching from the left side, the slope is not same. That's why there is a sharp edge, right? The slope is not same at that point.
Okay,
Between
so
approaching from the right and approaching from the left. That's why the sharp edge develops.
Okay, so that might be the
And
reason
mod
why
function is one of the example of that.
Okay.
Which has a sharp edge as origin.
Okay, so that might be the reason why we say that a curve is something which is not having any sharp edge, right?
Right. Right. So if a curve has no sharp edge at any point, that means it is differentiable everywhere. Right? The change of slope is smooth. The change of slope is, there is no sudden change of slope at any point. right? Here there is a sudden change of slope. So when we are approaching from the left side, when we are coming from the negative side, the slope was -1. But when we are coming to the origin, from the right side, the slope is 1. So at origin, there is a sudden change in slope, right? From -1 to 1. Right? That's why there is a sharp edge. And that's why it is not differentiable at that point. Okay? Clear?
Yes, sir.
So this limit does not exist. So in this case, partial derivative at 0, 0 does not exist. Is it clear? Is it clear? Partial derivative at 0, 0 does not exist. Okay? So can you tell me now what is about partial derivative with respect to y? Anyone? For y it is easy, right? So for y what we have to write? Limit h tending to 0. Can someone just tell me? What I
F
should write?
bracket 0 comma h.
Okay.
Divided
By
by
h,
h.
right?
Yeah.
So what is the numerator?
Mod 0. Mod 0.
Mod 0 is 0. So what is 0 comma f of 0 comma h?
It should be 0, na sir?
Will become 0. Yeah. Mod 0
Of 0
bracket
comma
1
h.
plus.
So mod 0 bracket 1 plus h. So it is 0 into something, that is 0, right? So 0 minus this is again 0 by h. So it is.
So finally 0.
So with respect to y, the partial derivative exists, but with respect to x, partial derivative does not exist. Okay, clear?
Yes.
So
sir.
this is one really good example for such a case when one partial derivative exists and another does not. Okay. So let me show you the graph of this function. Not this one, this one. So this is the graph of mod x into 1 plus y. Okay. You can see how this graph looks like. So you can see that this green one is the y-axis, sorry, x-axis, the green line. And there is a sudden change in slope of this surface along x-axis, right? There is a sharp turn at this point, right? So if I draw, say what should I draw? XZ plane, right? So if I draw y equal to 0, it will be with this line. Yeah. So this. So you can see this plane will just intersect the function at x-axis and nowhere else, and there is a sharp change from the right and the left of this plane, correct? Can you visualize it? There is a sudden change of the behavior of the slope at the left and the right of this plane. Can you see it?
Yes, sir.
Right? Everyone? Okay. So now
Yes, sir.
let remove this. So okay. So if I try to calculate the partial derivative, okay, except origin, we don't really need at origin. First, try to calculate the partial derivative in general. Okay, so at other point it exists. So these two planes we are getting, which are giving me the partial derivative at different points. Okay, so you can see that slope of these 2 points are different, right? One is left inclined and one is right inclined. Correct?
Yes, sir.
Yes, sir.
That's why at those points, I mean at origin or those points, the partial derivative does not exist. Okay? Because at origin, see at 0, what is the value, I mean, where the plane intersect the z-axis? It is 1, right? Here. Can you see it? And around this is minus 1. It is intersecting a minus 1 here. One is above z-axis, another is, I mean, along the positive direction of z-axis, another is along the negative direction of z-axis, right? So if you are approaching to 0 from the right side of this x-axis and right side of the left side of this x-axis, we are getting two different values. One is 1 and another is minus 1, which is exactly we are calculating here, right? This one is 1, another is minus 1. This is mod h by h, right? So from the left side, it is minus 1. From the right side, it is 1. This is exactly what we are seeing here. Correct? Here it is coming to 1. And if you see it below, near origin, it is coming to minus 1. Here. Is it clear? So at origin, it has two different slope. So partial derivative does not exist at origin. Is this visualization clear? I mean, at least you get the concept. What is going on here? Everyone?
Yes, sir.
Okay. Do you have any doubt? You can ask me till this point.
So basically, in order to that partial derivative is continuous exists at a point, we have to prove that the partial derivative is continuous, right?
Partial derivative, continuity of partial derivative is different issue. I mean, that is more involved. But this is the first question, basic question, whether partial derivative exists or not. So in this case, we are saying partial derivative does not exist at all at that point. So we are not even talking about continuity. It does not exist. It is more basic. Okay.
So we will check for the right.
What you are saying is basically the function we are getting after partial derivation, that function is not continuous at 0. What
yes,
you are saying. But
yes,
my point is, does not continuous is far beyond. It is not exist at that point itself. Okay. So at 0, 0, we cannot even calculate what partial derivative is because it does not exist. Okay. We just only see when we are approaching for the left, it is coming to minus 1. When we are approaching for the right, it is coming to 1. That only we can say. But exactly at 0, 0, what is the output we don't know because the function even does not exist there. Am I clear? Is it clear?
So what if the function had been defined as such that at origin the value of the function is 0? In that case, what would we say about the partial derivative? In that case,
still partial derivative does not exist because the limit should meet at that point, no?
Yes, sir. Okay, sir.
So limit does not exist. Yeah. Yeah. Any other doubt? So if you don't have any doubt, so I assume that till partial derivative, everything is clear, right?
Sir, this part is clear, sir. But while watching lectures, sir, a term is being used quite frequently, that open ball concept, sir.
I will come to that.
Okay,
till now, we don't really need open ball. What I have discussed.
Sorry, sir. I thought. Okay, no problem.
Yeah. I will definitely define that. Okay. So let me go till directional derivative at least. Then I will come to that. Okay. Because at least I will try to enter till week 11 today. Because we are still, week 10. Because we are still on week 9. Yeah. So this is the multivariable function defined on the domain of R3. What will be the partial derivative with respect to x and y? So what we should do when we are calculating partial derivative with respect to x, we will have to fix y and z. So basically we will treat y and z as constant, right? So what is fx x comma y comma z? We will take the derivative of x only and make y as constant, y and z. So if y is constant here, it is only y
y
because
plus 0
y plus this is 0 and
plus
then
z
this is z and then
minus 3yz.
minus 3yz. Great. So f of y, what is f of y?
X
X
plus z
plus z
0
ah,
and then minus 3xz.
okay. Great. So this is how we generally calculate it if we know the partial derivative exists. But if some question is asked whether partial derivative exists or not, or if a function is defined like using mod function or using like this, I mean like by parts function, by piecewise function, in those cases we have to check whether partial derivative exists or not first. Then we can calculate it. Okay. Okay. Now the same concept as we are discussing earlier, that why only we are talking about axes. I mean, why are we only talking about those axes? We are only x-axis or y-axis or z-axis, all this. Because we can consider unit vector in any direction and we can do the same thing for that, right? So in that, for using that concept, we are introducing what is called directional derivative. Now, directional derivative means what? Suppose I have a function and I have taken any unit vector. See, here unit vector is really important. Unit vector means the norm should be 1. You know how to calculate the norm, right? And here, when we are talking about norm, we are talking about the usual norm. That is the length function. Okay? Square root of u1 square, u2 square till un square. Right? That should be 1. So if we consider that unit vector, and then along that unit vector, how directional derivative is defined. So this is again same. We are taking x. Suppose at the point x, which is x1 to xn. So let's say a vector, which is a1 to an, and my unit vector is given as u1, u2, un. Then we are to calculate this and this vector a. So we can. So what is this? So basically, limit h tending to 0, f of what we should do, a plus h u minus f of a by h. The same type of definition we will use. Now what is this? What is a plus h u? A is a vector, so I can write is a 2 to n minus h of u1 to un. So this is basically h plus a1 plus h u1, a2 plus h u2, and so on, an plus h un. This is the new vector we are considering. So we are shifting a by h u, and so this definition will become limit h tending to 0, f of a1 plus h u1, an plus h un minus f of a1 to an, the same point, and we are dividing by the shift. If this limit exists, then we say directional derivative along that direction exists, and then we can calculate it like this by this limit. Is it clear? The definition is clear at least?
Yeah.
Okay, great. Okay, so let's see. Yeah, so we have a question like this. A function is again defined like piecewise function, and we have to calculate the directional derivative at the point 0, 0. That means at the origin, and the vector, unit vector is given as root 3 by 2 comma half. So first of all, is this unit vector? We have to check whether this is unit vector or not. Otherwise, we have to make that vector to be a unit vector. Okay. So is u a unit vector?
Yes,
That
sir.
is the first question. Yes, right?
Yes.
Because norm of u is root over root 3 by 2 whole square plus half whole square. So this is
3 by
root
4.
over 3 by 4, 1 by 4, so 4 by 4, that is 1, right? So you indeed a unit vector. So we can work with that. So limit h tending to 0, f of 0 plus, so let me write it like this, 0 comma 0 plus h root 3 by 2 comma half. This is the first portion, this is the second portion by 8. Correct? This was the definition we have taken. The vector a h into u minus f of a. So this is the thing we are talking about. Limit h tending to 0, f of h 3 by 2 comma h by 2. F of 0 comma 0 is 0 because at x equal to 0, y equal to 0, it is 0. So I should not write it and like this. So now what is the value of the first one? At x it is h root 3 by 2, at y it is h by 2. So x square y. So h square into 3 by 4.
Square by 4.
Into
X by 2.
2. Right? By, what is this one?
2 times
X power 4.
9h4.
Root 3, 9 by 2 power 4 plus h square by 4. Right?
So h4 by, that's y square. Yeah.
Is it correct or
Yes,
have I made any
correct,
mistake?
Sorry, it's y square. Yes, correct.
Yeah, okay. Great. So, yeah. What is this now? So, this is 3 by 8 h cube.
What you did, sir, in previous step in this one?
This is my x and this is my y. So, I have put the values here.
Okay. Got it.
This is the function, right? This is the function.
Yes, sir, yes.
So, we have just put the value. So, check whether I am doing something wrong or not. I mean, this is quite calculative.
Sir, but formula is f of h comma 0, I think.
What?
Sir,
Can you repeat?
Sir, in first question, which formula you used?
No, this is my directional derivative, right? Okay. F of h into u minus f of a. Right? So here what is u? U is this one, right? This is my vector.
Okay.
So 0 comma 0 plus h into u minus f of a. A is 0 comma 0. So this is my a. This is h. This is u. This is a. So f of a plus hu minus f of a by h. Okay? Along the vector u, what is the change? That is we are talking about. Okay? So, have anyone calculated it? What is this? No? I have to do it. 9h power 4 by 16 plus a square by 4 into 1 by h.
Cancel h square. You can pull out h square, no?
So, what is this?
Can we take out the h square?
What you are saying?
I was saying, can we cancel out h square, sir, from the first steps?
I will do that all together.
The limit is 3 by 2.
Is it? Okay. Anyway, so let me do it. What we are doing. So we can take h square common from here. No, one h will be.
Yes, sir. This h will cancel h cube, sir. So it will become h square.
So h cube will be cancelled, right? Total.
No, not. Yeah. Yes, it will be cancelled total.
So 9h square plus 4 by 16, like this, right?
Yes.
Yeah. Okay. So what I am getting, limit h tending to 0. Now put h is 0 itself here because there is no other h. So 3 by 8 by 1 by 4. Okay. So 3 by 8, 4 by 1, 3 by 2. Yeah. So this is the answer, right? So basically you got the idea. This is just a calculation. Basically you got the idea how we should calculate the directional derivative and what does it mean. Okay. So this is kind of generalization of partial derivative. Partial derivative, what we are doing for partial derivative, we are basically calculating the directional derivative, but with the unit vector 1, 0 or 0, 1 in case of x, y, x-axis and y-axis. Instead of that, we are taking a general vector. Okay.
And so if it is not 0 at s0, y0, then we have to compute that value. We have to put that value. Right?
Exactly, we have to put that value. Yeah. So things to remember is that directional derivative is generalization of partial derivative. Is that part clear? Instead of 1, 0 vector, we can take any unit vector, basically. That is our directional derivative. So partial derivative is one of the directional derivative. In that case, the unit vector is 1, 0 or 0, 1. The standard.
What we're saying is partial derivatives are in the direction of the axis, right? Limited to axes.
Exactly.
And in the directional derivatives, we can take any vector, unit vector, in any direction, and in accordance to that, we calculate.
Exactly. Correct. Correct. Is it clear? Everyone, is it clear?
Yes, sir.
Okay, great. Okay, so now another important thing which we came across in week 9 is gradient of a function. Now we have already learned what partial derivatives are. So if we take a function from Rn to R, Rn to R, so basically we are taking n variables here, x1 to xn, and with respect to each variable, if we calculate the partial derivative, f of x1, f of x2, till f of xn. If we calculate this, and if we got this vector, so this is called my gradient of a function. This vector we call it the gradient of the function. Okay. Now here the concept of open ball is coming in the picture. So let me see what an open ball is. So before going to the open ball, do you remember what an open interval is in R? Suppose this is my real line. Okay. Here some was 0, here 1, and so on, -1, -2, and so on. Okay. So if I say an open interval, so open interval notation was like this. So -2, 1. What is this open interval? What is this set basically?
It is taking
The
value
end
from
points
-2 to 1 and points included.
Yes, yes.
So boundaries are
-2,
included, that's
Not
what you're saying,
included.
right?
Open
Not
is
included. Not included.
Not included. Correct.
Yes.
So this is basically the set of all real numbers, which is strictly greater than -2 and strictly less than 1. Okay. These are strictly greater and strictly less. Okay. So -2 and 1 is not included. Correct?
Yes.
Okay. So if I say now, is this open interval is an interval containing 0?
Yes.
Yes. So if I tell you that -2, 1 is an open interval containing 0, that is a correct statement, right? Similarly, -1, 1, this is also an open interval containing 0.
Yes, sir.
Yes, sir.
So we can make it more smaller. We can come closer to 0 and take like this open interval. Okay. So basically we can create infinite number of open intervals containing 0 like this. So basically what we are saying, in the neighborhood of 0, we are taking some points and considering an open interval around 0. Okay. So in R, this statement, what does it mean? It is clear, right? Similarly, if we come to R2 now, okay, in R2. So this is 0 is not anything special here. We can do it for any point. Okay? So if I consider you this point A, any real number A, by around A, in the neighborhood of A, we can consider some open interval, right? So I can consider A plus 1 and A minus 1. This will give me an open interval, right? Around A, correct? This is one of the open intervals. There are infinitely many open intervals, but this is one of them. Okay. Now, suppose in case of open ball, if we say 0, 0, this is the origin. Now, if I want to, consider the neighborhood of 0, 0, will an open interval, enough? Just an open interval, is this enough?
Both directions.
Just this one. Is this open interval enough?
No, sir.
All the dimensions are not covered.
No, sir.
All the dimensions are not covered, right?
Yes.
So along this y-axis also we have to take something, right?
Sir, could you please come again, sir? Sorry.
So we want to see the neighborhood of 0, 0. Yes. Neighborhood means who are sitting in the neighbor of 0, 0.
Yes.
Right? So if we try to see all those points, some neighborhood of 0, if we want to see that, is an interval along x-axis or some interval along y-axis, is that enough?
No, we have to consider both.
Right? We have to cover all the dimensions, right?
Yes, yes.
From all the direction we have to see that, right? Yes. So not only these two open interval is not enough, because here also we want to see something, right? Along all the directions, right? So what we can do? Any idea what we can do? Anyone?
So it can be considered as a sphere with center as the origin.
So here it is not sphere, so we can take a circle because it is R2, right? If we consider this circle,
yes, sir.
Right? If you consider
for
this
R3
circle,
might be a sphere.
Exactly. R3, it is a sphere. Yeah. So we can consider this set. So suppose I am considering this circle. So let me write one set, which I have already written at the beginning of this session. Right? Not exactly this. We have written its boundary basically. X square plus y square equal to 1 we have written. Now basically what I am saying, forget that boundary. Okay? Consider all the points inside that circle. That is an open neighborhood of 0, 0 in R2, right? Is this clear? So if we want to see a neighborhood of 0, 0, we can consider a circle around 0, 0 of radius 1 without the boundary because we want to make it open.
Yes.
So this is the generalization of open interval in R in terms of R2 and so on. So we will come R3 and R4 later.
So if we take boundary, then what will go wrong, sir?
If it is?
If we take boundary, okay, so we will
no, there is nothing wrong with the boundary, but we are only trying to generalize open interval. That's why I am calling it open.
Okay.
There is a point why it should be open, but I will mention it later. Okay. First, at least understand whether it is a generalization of open interval in R2 or not.
Yes, this is crystal clear.
This is clear, right?
Yes.
So if we want to, see the neighborhood of 0, 0, we should consider something like this. Okay. Yeah, you can argue that you can also take some square like this, open square. We don't take the boundary. Then also we can see the neighborhood of that. But it is what is called? It is the convention that we always deal with these circular things. Okay, circle, sphere, all these things, because it is easier to deal with that. Okay. Even why need some specific geometrical figure? You can just consider 0, 0 some neighborhood like this. This is also done, but you can always see a circle inside that. You can always place it like this, right? So it is enough to deal with the circles. That is my point. And the set is easier to write, and we can deal with it quite easily. That's why we are considering open circles. Okay. So in R2 it is clear. Now what happens if we go to R3? Suppose we want to see the neighborhood of this origin 0, 0, 0. Now what we have to consider now? A sphere, right?
Yeah.
A sphere around this. Right? An open sphere around this. Correct? X, Y, Z such that x square plus y square plus z square less than 1. Okay? Clear? So what is basically a sphere? Sphere is like a ball, right? Sphere is nothing but a ball, right? So now till R3 we have named it a sphere, but in case of R4 we don't have any particular name for it, correct? So we call it n ball. So in R4 we call it 4 ball, in R5 we call it 5 ball, like this. Basically n represents the dimension in which we are talking about, and the set for n ball we can write this as set at x1 to xn such that x1 square plus x2 square till xn square it is less than 1. So ball of radius 1 in n dimension. That is our open ball. Is it clear?
Yes.
Is this concept clear, everyone?
Yes. Yes.
Okay. So now two questions remain: why we are considering open, and why we are considering circular thing. I mean ball type of thing. So ball type of thing I have already answered that it is easier to deal with. We can write the set more clearly here. That is one reason for considering it ball. And whatever the geometrical figure you consider around 0, we can place a ball inside that. That is the idea. And why open is required? Because again, we have to go to higher mathematics where some topological figure will come in the picture, and all the topology are basically dealing with either open or closed, any one of these. So if you only consider open, then we can generate a topology and do it here. So that's why open is needed. If you don't understand this statement, forget it. We don't need it here. But there is a reason why we are considering it open. That is my point. Is it
Even
clear?
like, yes sir, clear. Even sir, like we are taking less than 1, we can take any value.
Yeah, we can take any value. Yeah, I mean one is not clear. I mean this is one open ball. I mean we can take any a here, which is where a is greater than 0.
It
That
is not
should be the
sacrosanct.
perfect.
It is not sacrosanct. We can take any value. Yes.
Exactly. So a should be greater than 0 at least. Otherwise it will just come to 0. Is it clear?
Yes sir.
Okay, so this is in all places, right? Here all should be a. I have just considered on the ball which are radius 1, but actually it is radius
Very well
a root a
explained, sir.
where
Thank
a
you.
is greater than 0.
Very well explained. Thank you, sir.
Okay. Okay, so you can see the similarity how we are coming from R2 R2 to R3 and then Rn. Okay, that's what open ball really does. Okay.
Sir, in higher dimensions, it's always be x square only, sir, for the open ball concept. Or we can consider the other terms also.
No, this ball means always it should be equation like this: x square plus x1 square plus x2 square plus x3 square, like this. That is you are asking, right?
Yes, I'm asking that one.
Yeah, that is the equation of ball, because along each direction the radius should be same, right?
Yeah.
So
like
this
how
is the
we
generalization.
come to conclusion like it's for the higher dimensions, like as mentioned in the n. So it's x square, y square. Are we generalizing from the
No, you can
plane to
visualize it
sphere?
basically. See, for R3, okay, suppose you want to take a ball of radius 1, okay, So at least you have to this 1 comma 0 comma 0, 0 comma 1 comma 0, and 0 comma 0 comma 1. At least these 3 points should be on the boundary, right?
Yeah, yes.
Now can you visualize it? Why we require this type of equation? This is one visualization I have given you. This is not exactly how the equation comes, but at least you can visualize it, right?
Yeah.
Because at two places you are putting 0, and also the negative you should consider into account. Okay, let me write it what I am saying.
Like I have understood, like in the like circle in the sphere, we are enclosing all the points. So all the 3 points are falling into the sphere.
Okay, so let me do it for R4. Okay, if we in R4, if it is a ball of radius 1, okay, so suppose R4 I cannot draw, so forget about drawing this thing. But these 2 points should be on the boundary, right? Must be in the boundary of radius 1, because from the origin both of these two distance of these 2 points is exactly 1. Correct?
Yes, sir.
This is clear, right?
Yes, sir.
Yes.
Now the equation must satisfy this point and this point, right? At least this is at least you know. And now you vary this. Now 0, 1. This also 1.
Yeah.
This also 1, right? Correct? Now this also 1. This also 1. Similarly for the third one.
So we are deducing from the distance concept, distance between
exactly,
the 2 points.
Exactly.
Okay. Okay, sir.
Because all the points which are at a distance of radius 1, that should be there. No?
Okay. Okay, sir.
So suppose I am now come to the figure. Suppose I am taking an arbitrary point, x1, x2, x3, x4. Okay, this is an arbitrary point and origin. The distance of these 2 points should be 1, right? Now what is the distance between these 2 points?
Plus x2.
Correct?
Yes, sir.
Root over of that should be 1, right? So I have taken an arbitrary point, right? And what is the equation I am getting? Right? Squaring both sides, right? And we have started with the arbitrary point. So this is the equation. Yeah.
Okay, sir. Yes.
Okay, great. Okay, so yeah. So when we are using multivariable calculus and we are talking about neighborhood, always remember we are talking about some open ball around that point. Okay, and depending on the dimension, we should consider, is it a circle, is it a sphere, or is it an n-dimensional ball? Okay. So now if this gradient f exists and is continuous in the open ball around that point, around the point a1 to a2, then the directional derivative, this is one important theorem which we are talking about. So then the directional derivative of the function at that point in the direction of the vector v is given by the dot product of the gradient function at that point along the unit vector in the direction of v. So what does it say? So we have seen how directional derivative is calculated using the definition. Okay, f of a plus hu minus f of a by h. That was the definition of directional derivative. Now this theorem will give us a shortcut method, we can say, to calculate the directional derivative at any point along any vector. What is the method? So using the definition we can calculate it, but sometimes it may be really hectic to calculate that. But this theorem will give us a easier method to do that. So what is the condition of this theorem? We cannot apply this theorem anywhere. So there is some hypothesis. First hypothesis is this gradient f, this should exist. This is the first condition. Second condition, this is continuous in an open ball around A1 to AN. So what is A1 to AN? A1 to AN is the point in which we are calculating the directional derivative. Okay, so if we consider an open ball around that point, in those neighborhood, this gradient f should be continuous. What does it mean that gradient f should be continuous? We know that gradient is a function, right? So each coordinate, this fxi, fx1, fx2, fxn, all these should be continuous. Okay, in this interval, in this open neighborhood. Okay, so this is the thing which we are talking about. So and the directional derivative, so the how will, if these two conditions satisfied, how we will calculate the directional derivative? We will calculate the gradient and we will consider the unit vector along the vector which is given. Now the vector which is given may not be unique, so we have to normalize it to make it a unit vector, and we will take the dot product with it. Okay, dot product of the gradient vector and the unit vector. And unit vector means normalizing the vector which is given. If we can do it, we can, what we get is basically the directional derivative along that vector at that point, if these two conditions satisfies. Is it clear? What does this theorem say?
Yes, sir.
Okay. So first of all, we have to check whether grad f exists or not, and secondly, we have to check whether grad f is continuous in the open interval. Okay. So in general, these two, I mean, for the simple function which we are generally talking about, these two generally satisfies. Okay, so it is does not satisfy for some complicated function, but okay, those cases we have to consider, but in general for simpler function it is satisfied. Okay, so basically we have to calculate the gradient of the function, and we have to calculate the unit vector along the direction in which we have to calculate the directional derivative, and we have to take the dot product to calculate the directional derivative. Okay, so let's see an example. No, this is not that. This is some different thing. Okay, so this I will come later. This is near approximation. Okay. Okay, so let us consider this function, x square plus y square plus x square y. Okay, let us take this function. Okay, so and say we have to consider along the at a point 1 comma 1, this is the point along the vector what should we give? 3, 4. Okay, so if we want to calculate the directional derivative of f at a point 1 comma 1 along the vector 3 comma 4, how we should calculate the directional derivative? Now one way we already know using the definition, and other way we just now have seen. So let's first see what that how that we can do. So we have to first consider the gradient of the function. Now what is the gradient? Can someone tell me what is the gradient vector?
Partial derivative with respect to x and partial derivative with respect to
2xy square.
Okay. 2xy square plus
2xy.
X square.
No, first you have to with respect to x, right?
Yeah.
So
Yes.
2x,
Yes.
2y
what
x
is the
square.
2x
x
square
2xy
plus x.
X square.
Point 1 comma 1 4 comma 3 will get the.
So I will come to that. Now we have to verify these two hypotheses is satisfied or not, right? We have taken two hypotheses. Now grad f exists. This is clear, right? Because this is a polynomial type of function, and grad f is continuous because both the coordinate are continuous function, because those are polynomial in terms of x and y. There is no point of discontinuity, right? So we really don't have to bother about the discontinuity of this gradient function. So we can apply the theorem, right? Now what is the theorem saying? So grad f at the point this what is this? We have to put x and y here. So this is 4 comma 3. Correct? This is grad of f at the point 1 comma 1. Now this is my vector v. Right? What is this vector a unit vector?
No, no, sir.
No. No. So we have to divide it with norm. What is this norm?
5.
Norm is 5. So v by norm v, that is 3 by 5 comma 4 by 5. Now it became a unit vector. Correct?
Yes, sir.
So what we have to do? The directional derivative at the point along the vector v at the point 1 comma 1. Now it is grad of f1 comma 1 dot v norm v. Now what is this? Grad is 4 comma 3 dot 3 by 5 comma 4 by 5. So what is this? 12 by 5. This is dot product. So you know how to do the dot product. 12 by 5 plus 12 by 5. This is 24 by 5. Is it clear? So this is the directional derivative at that point. Okay?
Sir,
Yeah.
is there a name for such functions?
Which function?
With such degrees x y x squared x y. For example, had it been only in one variable, we would have said it is a polynomial in x.
This is polynomial in x and y.
Okay.
Same thing, polynomial function in x and y in two variables. Okay. Similarly, for three variables, we can call it polynomial function of three variables. Right? There is a concept of polynomial function of n variable. Right? So
here, so one doubt is here when we have the f of x y, x square, y square, plus x square, y. So del f of x y. So derivative first we are calculating derivative with respect to x and then with respect to y. Is it how do we get it?
The first one is derivative with respect to x. This is fx and this is fy.
Okay, first we will do the partial derivative with respect to x, and second is the partial derivative with respect to y.
Exactly. That's how gradient is defined.
Okay.
This is the definition of gradient. This one. This
Sir, can we visualize into the 3D plotter, sir? Like you have
gradient, right?
Yeah, this problem you have mentioned, the gradient.
Actually, I was going to give a visualization of gradient, but before that, I think if we complete the tangent plane, then it will be easier to explain. Okay. So when I will come to tangent plane, then I will do it. Is that okay?
Okay, sir.
Because gradient has a relation with tangent plane.
Okay, sir.
Can you just scroll up for a bit, sir? Just have a look at it, sir. Not more later, but I just want to see the steps. Scroll a bit up. Can you scroll up to the previous page, sir, just for a second? This is not much, sir. Just near the derivation. Yes, sir. So here, basically at 1 we have to calculate the derivative.
Yeah. Calculate the gradient.
Along gradient and along the vector for 3, 4 or 4, 3, 4.
3, 4, 4, 3 we are getting. That is the gradient at 1, 1.
Okay, we are getting 4, 3. Okay, along 3, 4 we have to calculate. Okay.
Exactly.
Sir, when we calculated fx and fy, then it is becoming gradient function. And the moment we plug the value of x and y, then it is becoming gradient value, right?
Gradient vector, yeah.
Gradient vector.
In general, gradient is a vector value function. Okay. Gradient is taking, so in this case, this is from R2 to R2, right? Because we are taking input from R2 and giving input in R2. So it is a vector value multivariable function.
So this is gradient function, and the moment we plug the value of x and y, then it is becoming gradient value.
We will get a vector.
Yeah, vector. Sorry, gradient vector. Yes.
Exactly. That is the case. That is for any vector value function. That is the case, right? So if you go to the beginning of this session, I have to scroll it up. Yeah. So vector value function means what? It is from
vector value function.
From some domain in Rn to Rm, right? So suppose this is R2 to R2, right? So this is taking input from R2 and giving output in R2. Now if you put any one value, suppose 1 comma 2, the value you will get as an output, that is a vector in R2, right? That is true for any vectorial function, and gradient is one of these vectorial multivariable function. Gradient is an example of this vectorial multivariable function. Okay? Clear?
Yes, yes.
Okay, great.
So could you
Gradient
please
is
do
always from Rn to Rn, right?
Yeah, right. Gradient is always from R into R. Correct. I mean, n can be different, but yeah.
so
Hmm.
so could you do one sum please?
Which sum?
That x square y by x square plus y4, that function using this.
Okay, but in that case, is gradient vector continuous?
Yeah, yes sir. So that is what I want you to do.
Okay, have you done it?
The,
Yeah, tell me the function.
yes sir. So f of xy was x square y by x square plus y to the power 4 when x y not origin and 0 otherwise.
Okay. So what is the gradient and which
So at 0 0
at 0 0 we want to calculate, right?
yes sir.
So at 0 0 is partial derivative exist? Have you checked that?
Yes sir, that is what I want to know, how to check that.
You know how partial derivative exists. You have to check, right? So this is for x, right? Does this
Yes,
limit exist?
yes sir, this will be 0.
This will be 0, right? So
Yes,
let me check once. This will be 0 because this is h and this is 0. Anyway, this is h square 0. So this is 0, and also for the second one, this is 0, right?
yes sir.
Okay, so basically, gradient of f
At 0
at
0.
0 comma 0 is 0,
Yes, 0
right?
comma. So
Now,
whatever
what is the gradient in general
uh,
when it is non-zero?
so that we have to find
Check it. What is
uh,
fx and fy,
each.
and then you can check whether the limit value matches with that 0 comma 0. Right? That is the usual way of checking, right? This is fx comma fy. What is fx? What is fx? This is f. So what is with respect to x?
Plus y
So
for y for 2
Some complicated function will
x
come,
y.
right?
Yes, sir.
X square
X
2
plus
y
y
into
is
x square plus y power 4 y
minus something will be there.
minus
X
x
square
square y
2x, right? This is fx, right?
yes sir.
So what is this? And what is fy? Let do it simultaneously. So x
y
square
power 2 times
minus
to 4
sorry, x square
x square
minus x square y 4y cube, right? So it is not continuous basically, because when we are approaching to 0 comma 0, it is both the functions going to infinity or something.
So that is where I'm stuck. So
So we cannot apply this theorem.
no,
Right?
basically how to prove that this is indeed
See.
going to infinity or something.
So continuity we have done, right? In week
Yes
9.
sir.
Okay, let me do it for one function, then I will
Yes,
explain.
sir.
So x cube y plus 2xy power 5 minus 2x cube y, right?
Yes,
by
sir.
x square plus y power 4 square. Okay.
Yes, sir.
Okay. So let me give you how you can check this function is continuous or not. Okay.
Yes.
What is the maximum power above?
You can cancel the first term and the last term. Then it becomes 2xy 5.
Okay. Anyway, we don't, yeah. So this is, and there is some second function. Okay.
Yes, sir.
I think the first function is not continuous itself. So let's check. So what I am getting 2xy power 5 x square plus y power 4 whole square. Right?
Yes, sir.
Okay. So if I put y equal to mx, okay, if I am approaching 0 comma 0 along this straight line, so what does continuity mean? First and mean. Do you remember what continuity means?
Yes, sir. The limit exists for all.
Limit exists and it should be equal to
Equal to 0, equal to the value
f of
at
0.
that point.
Yeah. Right? So this should happen, right?
Yes, sir.
Okay. So first of all, check whether limit at 0 comma 0 exists or not for this function. Okay.
Yes, sir.
Okay. So if we apply y equal to mx, I think x will not cancel out, right? X was 6, and this is
Sir, it's 0, right? Yes, sir. It's 0.
it's 0. Yeah.
Yes, sir.
No,
Yeah.
why 0?
So because it's x to the power 6 above, and
Hmm.
so we have m to the power 5 there. Then we do x tends to 0. Then the numerator always goes to 0.
M power 5 x power 5 x square m power 4 x power 4 square, right?
Yes, sir.
So 2x power 6 m power 5, and here I can take x square common, so x power 4,
Yes.
right?
Yes, sir.
X square whole square. So x square should be there. So along this curve I will not get anything. Along this curve it will
Yes.
go to 0.
Now
But
this
we
is
have to
where
find different curve.
yes, sir. So this is where I'm facing problem in finding limits of
Finding which curve will satisfy this, right?
rational functions.
Yeah. So let me see. So one easy trick first I can suggest you, that is what is the degree of the numerator?
6.
I mean, how we can see check it directly. What is the degree of the numerator?
Size 6.
6, right? And what
Yes.
is the degree of the denominator?
Size 8.
8. So denominator has
8.
more degree, right? It is a
Yes.
higher degree.
Yes, sir.
So when we are approaching towards 0, so it is basically suppose in single variable, like x square by x power 5.
Yes,
Okay.
sir.
So what is this basically? If we cancel these two, we'll get something here,
Yes,
right?
sir.
X cube.
Yes,
So
sir.
when we are approaching towards 0, it generally goes towards infinity, right?
Yes, sir.
Same thing is happening here.
So,
Okay.
sir,
If
will
you
this work
cannot find a particular curve directly, this is one approach you can take to tell that it is not exactly continuous. That you
So,
can say.
will this work for all rational functions?
This generally work for all rational functions for telling whether it is continuous or not. But limit still may exist. Okay. I am not sure whether the limit of the function exists or not. Limit may exist, but I don't know. But it generally is supposed to be not continuous. Okay.
Limits can exist. Okay, sir.
I mean, for some rational function, limit can exist, but generally it tells you whether it function is a continuous or not by seeing the degree of rational function in the numerator and denominator. Okay.
So, at 0, we can say that limit may not
Yeah,
exist.
at 0 only. Yeah, right. Otherwise, we cannot say.
So, at 0, will are there cases where limit can exist?
No, no,
Even if
no,
it
no, no,
differ?
no. At 0, limit does not exist.
Okay, sir.
Because it's going to infinity, I think.
Yes, sir. But suppose it had not been at 0, 0, then this wouldn't
Then
imply
it is
that.
continuous. Then it is
Oh,
continuous.
then it is continuous.
Then it is continuous. Okay. The problem is that 0, 0, 0 itself.
Okay, sir.
Okay. But we have to, if we try to find a curve, still we can do it.
So there was
Say,
an easier example where we could figure out from the expression that root x would work, but here I can't find any.
so what happen if we take x equal to some y, function of y? Have you checked it?
Yeah, what
X.
function should I take? That is the problem, right? Linear, it's working. Now, non-linear is difficult to reach at.
Yeah, that is the case. Because it's going to infinity. That is the case. Because limit does not exist in not that sense whether the limit is unique or not. Limit does not exist in the sense that limit is going to infinity. That's why finding a curve is not a easy task. Maybe there is no curve basically. Because for all the curve, limit is going to infinity. Do you get my point? What I am saying?
So how is that? Because of the
Finding a curve when works. Finding a curve gives us basically limit is not unique at that point, right? For
yes,
different curve, we are getting different values,
limit.
right? But
Yes,
here
sir.
the problem is here when x and xy approaching towards 0, the function is approaching toward infinity, and that is happening for any curve, right? So finding a curve will not give a solution for this. Do you get my point? What I am saying?
So can you repeat?
Suppose, yeah, suppose I am saying 1 by xy, okay? Limit xy tending to 0, comma 0. Here limit exists or not?
So it does not.
Does not, right? But you
Yes.
can, by finding a curve, you cannot tell it, right?
Yes, sir.
Because for any curve, limit will go to infinity, whatever
Yes.
curve you choose,
Yes, sir.
right?
Yes.
So finding a curve works only when the limit is not unique at some point.
Yes, sir.
But here limit is going to infinity. So uniqueness is not an issue here.
Yes,
Okay.
sir.
Got my point now? Similarly, this is happening in this case. This function. Here, the limit is going towards infinity. So finding a curve will not give you a solution for this. Okay.
So there was one more function like this. That was xy by x square plus y square.
Okay.
That seems easier, but even that I
That
couldn't.
is because for that case, basically, I mean, both the numerator and denominator had degree 2, right?
Yes, sir.
So it is not going to infinity, right?
Yes.
But here the issue is with the uniqueness of the limit.
Yes, sir.
That's why finding a curve will give a solution. If we can consider y equal to mx, then we will get the desired thing. I mean, get the thing what we desire basically.
Yes, sir.
Right? For different value of m, we will get different value of the limit. Right? But can you see the difference between these two now? For
Yes,
this,
sir.
when we are approaching towards 0, the function is approaching towards infinity.
Yes, sir.
Okay. But when we are approaching towards 0, in this case, function is not approaching towards infinity. Here, for different curves, the function is approaching towards different values. Right? Here is an issue with uniqueness. That's
Yes.
why finding a curve will give you a solution. But here, finding a curve will not give you a solution. Here, the limit itself is going to infinity.
Yes,
Okay?
sir.
That's why we are saying limit does not exist here. That is, the function does not continuous. Function is not continuous. Okay?
So probably, so it's safe to say that a limit won't exist at origin when the degree of the denominator is higher.
Right.
Okay. Sir. Because it will for any curve it will go to infinity.
Yeah, exactly. Exactly. Okay. Clear,
Yes.
no?
Yes, sir. Thank you.
So basically, we cannot apply this theorem here. Right? Here,
Yes.
if you want to calculate the directional derivative, you have to go through the definition, and also then you have to check whether that in that definition the limit exists or not. So that thing is remaining to check. I mean, whether the directional derivative also exists or not, that is a question. But if you want to calculate the directional derivative, here you have to go through the definition.
So can you just jot down the steps that needs to be done? So first of all, let's say suppose u1 and u2 is given as the unit vectors, then we have to find With respect to u1, u2, the
No,
direction.
one unit vector. Suppose a function is given.
Yes, sir. I'm saying the
A
coordinates
point
are
is
u1,
given.
u2.
Suppose a point is given and a
Yes.
vector is given.
Yes, sir.
Right? First, calculate grad of f. Right? Second, calculate grad of f means here substep is basically check all the partial derivative exist. Otherwise, grad does not exist, right?
Yes, sir.
All the partial derivative exist. Okay, if this satisfies, the partial derivative exists, then the second check is all the partial derivative are
Should be
continuous.
continuous.
Checks all the PD are continuous or not at A1, A2. Okay. Third step. So in this step, you are also calculating what this is, right? Otherwise, you cannot check continuity. So you definitely at this step, you know what grad of f at A1, A2. That you already know. So if this 1 and 2 satisfies, if 1 and 2 both are yes, then we apply the theorem. That means d of u f a1 a2 is basically grad f dot u
Dot U.
okay. Fourth, if either 1 or 2 no, I mean if either 1 or 2 does not satisfy, then go by the definition. Yeah.
Yes.
Great. So till this point, I think everything is clear, right?
Sir, along the line, we calculate directional derivative as 2x square m to the power 5. So what we conclude from this that the derivative
Which
is
one?
earlier when we calculate.
This one?
No. When we take for checking continuity. For checking continuity, we take directional derivative along the line y is equal to mx, and we
That is the directional derivative. No?
Yeah. So we get
This one.
actually 2x square m5. No,
This one.
Yeah. So we get 2x square m5. Then what we conclude from that the limit is 0 at
No, that's not what I am saying.
yeah.
I am saying is here what you can see. So the numerator and the denominator, there is a difference between the degree of numerator and denominator, right? For both degree of x and y are greater in the denominator than the numerator, correct?
Yes, sir.
So my claim is this function is basically at 0 is going to infinity. This is not continuous at that point.
Yeah,
So uniqueness is not an issue here.
Yeah, that part is clear. When we actually take along the line y is equal to mx, we get 2x square m5 in the last when we checking when we substitute for y as a mx, then we get 2x square m5. So for when the x approaching to 0, then we can say that the limit value is 0 there.
Along that curve?
Yeah, mx, yeah, y is equal to mx.
Along that curve, I think. So let's see.
Then we get 2x square m5, yeah. When we substitute
then it may be a issue of uniqueness also. Let's see. 2x mx5, right? This one, right? So 2x bar 6, m bar 5, x bar 4, x square, x bar 4, 1 plus m square x square. This one, right? So x
M
square.
raised
raised
to
to 4.
Yes, sir.
Huh? This one, right? So
Yes, sir. Yes, sir.
when we are taking x going to 0, this is going to 0. Yeah.
So we can say that limit exists here. Sorry,
Along this curve exists.
sorry, partial derivative exists here as a
No,
0.
this has nothing to do with partial derivative. This is
What?
what we think. This is the partial derivative with respect to x. This one.
Yes, sir. For
This is,
checking this is existing or not,
yeah.
we are
So
checking.
along
Along
this
this
y equal to
curve
mx.
only this, but there are infinitely many curves, no? So we cannot, by just checking only for y equal to mx, we cannot guarantee that limit is going to 0.
Okay,
Right?
sir. Actually, we get like 2x square m5, and when x approaching to 0,
But
then it
that is
is.
only for y equal to mx, but there can be many more curves, right?
Okay, okay, sir. So we can't say anything that.
Yeah, right.
Okay, sir. Yeah, it's clear, sir.
Yeah.
So how to, sir,
Pritam,
in this
1 minute.
case?
Pritam, are you there?
Yes, sir.
So basically, what here is the problem. Basically, for some curve, it may go to 0 also, as you are seeing.
Yes,
For
sir.
y equal
Yes,
to
sir.
mx, it is going to 0, but for some curve, it may going to infinity. So
Yes.
basically, there is a problem in uniqueness also.
Yes, sir.
Okay, not only infinity, but there is a problem in uniqueness also.
Yes,
I
sir.
forgot about this y equal to mx thing. Yeah. Okay.
So how to conclude about the continuity of this function, sir? Because
This is
uh,
not continuous. That's my point.
so
This is not continuous
how to prove that this is not continuous, sir?
because
Numerator
limit does
degree
not
is
exist,
higher.
no.
Denominator degree is higher.
So for y equal to mx, the limit exists and it is 0. Y equal
But
to mx.
for take different curve, then we will get different limit. Suppose I am taking what should I take?
Sir, y equals x to the power 4th, 1/4.
Y equal to x. So I mean x equal to y power 4. So,
Yes, sir.
okay. What I will get? Let's check. This is another curve, right? Along this curve also we can check our limit, right?
Yes.
Okay. So let's substitute here. What I will get?
Yes.
X square means y
Y
power
raised to 8. Y
8.
raised to 8.
And this is y power 4.
Yes.
So what I should get? Y power 4 should come out.
Yeah.
Y
Y raised to
power
8
4
should
will
come
not
out.
do, I
Y
think.
raised to 8.
So
Y
you can
raised to 8
divide by
will come out.
y to the power 9.
Y
So y
raised
power
to 8
4.
will come out.
And so the denominator is not.
No, y power 4 will not give me the solution. Say y power 5.
So from the denominator you remove y to the power 8. Y to the power 4 you take common.
Here also
So
it is going to 0. That is
yes,
what.
sir, it is going to 0.
So you are claiming that this is always going to 0.
I'm
Okay,
not
let me
claiming,
check.
sir, just to how to prove that. That's what I'm saying.
Let me check. Then there should be some method.
So there was some sandwich method which was used, but how to apply this sandwich method in this case? Earlier,
It's difficult because you can't see an expression to put it in. So we used the sandwich method mainly through a Cauchy-Squarce inequality, and here that is the case.
So let me think. Okay, so let me write this again. 2x y power 5 by x square plus y power 4 whole square. Have you checked using polar coordinate? Is it giving anything?
Please try y x square equals y.
X
I think
square
that
equal,
might work.
okay. Two x y is x square. So x power x square y power 5.
11.
So 10. Right? So total x power 11 basically here. No, I don't think it will work like this. Again, it will be come outside and go to 0. Right?
So denominator is higher. No.
Why?
1 minute, sir.
No. Some problem or mistake we are making here. We are making some mistake here. So let me first plot this in GeoGebra and see how it looks like. Okay. Can you tell me the function?
So 2x y to the
2x
power 5 whole divided by x square plus
1 minute. X square
plus y to the power 4 whole square. So denominator whole square.
with this. The screen is freezing now.
Two x y to the power 5 whole divided by x square plus y 4 whole square. So it's multiplied by 2, not squared denominator.
Oh, X square. At 0 it is not continuous, as you can see. This is indeed going to infinity, right?
So where is the positive x-axis?
This red one.
The positive part? So the right one is the positive part of x
This
axis,
side, this
right?
side.
Left side. Okay, sir.
Left side positive, right side is negative. Okay, and it is not continuous at 0. Okay. So there should exist some curve where it is not going to 0, but somehow I'm not getting which curve is it. So this is basically 2xy power 5. Here it is x power 4, y power 8 plus 2x square, y power 4, right? This is the function. So this is basically what am I claiming? This is greater than all the degrees. Anyone can suggest any function which by which we are not getting 0 here? Can someone try it?
Sir,
Yeah.
sir, if we put x equal to y square, then
X equal to y square. So this is 7, right? Okay. Plus 1.4. Then also it's going to 0, right? No? Oh no, I think. 2y power 4 whole square. That means 2y power 7, 4y power 8, right?
yes, sir.
Yes. This
So
is
then
limit
we
not
are not
exist.
going to 0.
Limit
Fine,
not
correct.
exist.
Right. Yeah, good. So yeah, definitely there is a function where it is not going to 0 and it is going to infinity. So at 0, the function, the limit basically does not exist here, and there are infinitely number of functions for which this function is going to infinity. And there are some function for which it is going to 0. So yeah, limit does not exist, and you can see that at 0, 0 this function is discontinuous or is absent. Okay. So is it clear?
Yes, sir. Yes, sir.
Good. Yeah. So let's move a little bit. So
Price has gone
till
down, sir.
this, huh?
Price has gone down.
What? What are you saying?
Sir, please mute all.
No, there is some noise outside my window. It will go away. Yeah. So what I am saying is, so till this point we have seen in week 9, right? And week 10 started with what is called gradient descent. So what is gradient descent basically? So we know what gradient means, right? Gradient means it is a vector element function fxy, grad of fxy. So we defined it like fx1, fx2 and so on. Now So let me try to give you a visualization how gradient defense basically works. So I hope many of you has gone to visit any hill or mountain, right, for some trekking or something. So suppose we have at some portion of the mountain, suppose I am here, okay, at the trekking I am here, and let's draw this mountain a little bit like so. From here I want to come down here. I want to come down to the below, I mean, of the mountain, the lower part of the mountain. Now suppose for some weather condition there is fog everywhere, so I cannot directly see what is the last point of this mountain. Okay, so from coming from here to here, which route I have to take I really don't know, because there are fog around me. So what generally we do, we'll see a small area, neighborhood around us, correct? We see small neighborhood, and at that small neighborhood will come what is the lowest point we can see till that portion, right? And again when we come here around the neighborhood, we will see what is the lowest point, and that way we may take some path to reach here at the lowest point. That may not be the optimal path. Okay, if we can see the whole picture from above, then we may know that there may be some other path which would be better to reach at the lowest point. But as we cannot see the whole picture from above due to the fog, so what we do, we will see the local property. Okay, the neighborhood around me, which is the lowest portion, and we come to that lowest portion, and again we will see the neighborhood around that that minimum point, and that way we will choose our path to come down to the lowest portion of the mountain, right? Now can we visualize this in terms of mathematics? Can we say what we are doing exactly here?
Directional derivative.
Directional derivative is one thing. Any other thing? So this is how local property actually works. Okay. So around the neighborhood, when I am not seeing the global picture. I am seeing the local picture. Okay. And at that local picture, I am trying to find the minimum point. Okay. So in this case, I am trying to find the minimum point. But when I am approaching toward the higher end of the mountain, then we will see what is the maximum point. Because at that portion, we have to reach to the top of the hill. So depending on our choice, we have to find out minimum or maximum. That is what we are doing. So basically, near that neighborhood, we have to find how the surface of the hill behaves. Where is the minimum point? And those minimum points are basically the local minimum which we are trying to find, right? So in those local area, in those local property, and along some direction, we are trying to find some direction where basically the steepness of the mountain is less, right? So that we can come down easily. Okay. So basically along that, we are trying to find that vector along which the steepness of the mountain is minimum, right? Or maximum in some cases. Okay, if it is required. So that is basically what gradient descent does. Okay, gradient descent also does. So we are at a point. So this point is my A1 to AN. In Rn, I am talking about. So we are at some point. We are seeing a neighborhood of E and trying to find a vector U along which the directional derivative is, directional derivative means what? The rate of change, right? The steepness. That is minimum or maximum, right? Is this concept clear? Is this clear to everyone?
Yes.
Yes, sir.
So it will be minimum, you said, right?
This is basically the concept of gradient descent.
So the directional derivative here, we would look for the minimum descent.
where the increase rate of change is maximum or where the rate of change is minimum. That is what we are looking for. Okay. So in the lectures, I has shown that how this will work, because basically directional derivative means what? If along this neighborhood, if everything is continuous, I mean the gradient vector is continuous along that neighborhood, then we have already seen the directional derivative is basically gradient vector at that point dot the unit vector which we are talking about. Okay, this is the thing we have seen, right? Now, when this is maximum, we want to find some vector when this is maximum. So basically, what we are doing, what this dot product do? So dot product of A dot B, what does it mean? This is
AB cos theta.
right? Norm A into norm B cos theta.
So we can say that in the direction of gradient vector, the value of
That is what
maximum.
I am going to do. Yeah, exactly. That is what we are getting into. So this is gradient. This is this. So dot u by this cos theta. Now basically a cos theta comes in the picture. Now what does it mean? It means that
When angle between the gradient vector and the vector in which direction we are taking the direction derivative.
Exactly.
Both are
So what is the maximum value of cos theta? When it will be maximum, when cos theta is maximum, right?
So basically,
zero degree.
Will it be the projection, sir?
0 degree, right? Yeah.
One
value.
No, someone is asking something else. What?
Sir, is it otherwise? Is it the projection on the direction, right?
So basically, yeah, when this cos theta is maximum, cos theta is maximum, when cos theta is value is 1, right? That is theta value is 0, right?
Yeah.
That is theta value 0 means what? The direction of the gradient, I mean, the gradient and direction of the unit vector should be the same.
Same direction.
So along the direction of the gradient, if we consider our unit vector, our directional derivative will be the maximum, right?
Yes, sir.
And when cos theta is minimum,
minus
180.
When angle is 180
degree.
degree.
It is exactly opposite, in opposite direction, right? 180 degree, right? So exactly in opposite direction. So along the gradient vector, if we consider our directional derivative, if we consider our unit vector, if we consider it along the gradient vector, then we will get the maximum directional derivative. And when it will be minimum when we will consider in the opposite direction of the gradient vector. Okay, is it clear?
Yeah.
Yes, sir.
Oh,
sorry, sir. Which will be minimum? Gradient will be minimum.
So
we are saying, right?
In direction of gradient vector, so when cos theta will be maximum, cos theta will be maximum when cos theta value is 1. That means theta is 0 degree. 0 degree means this gradient vector and this u, these two vector should be along the same direction.
Same direction.
Okay. So along grad f, this is maximum. DUF is maximum, right? And opposite to grad f, DUF is minimum.
Minus 1.
This is minus 1, so it will be minimum. And what is the value of maximum DUF?
Norm gradient. Norm of the
gradient, right? Because this will cancel out and this is 1, so this will be grad of f. And what is the minimum value of the directional derivative?
Minus norm of f.
Minus
norm of.
Minus norm of del f, right?
Yeah, exactly. Minus norm of gradient of f. This is not del, this is called nebula.
Sorry.
Grade is, so this is nebula.
So one doubt there. Can we say that at which point we are taking the directional derivative? if we take the tangent plane at that point, then this gradient vector will be perpendicular to that plane.
Exactly. So I have not reached to tangent plane, that's why I am not mentioning that. But actually that is the visualization. The gradient vector is the perpendicular to that tangent plane. Yeah,
Yes.
I will come to that. I will come to that. Okay. Maybe not today because today is already 3 hours.
Sir, shortly you will be uploading the same thing, sir, the annotated notes, because I wanted to see it later also. In the links, you will be shortly uploading after the session, na? This one?
I will upload this.
Live session link.
Yeah, sure. Yeah, so here is a question. Let's do it just first. So, particular frame of reference, the corner of hot rectangle. I think this is one of the problem in the activity question or practice somewhere. So, this is the temperature of the plate is given at Txy equal to x square y square plus x square y. So, from point -1, 2 in which direction the rate of change of temperature is minimum. That means what we have to find? We have to find a vector, the direction vector, along which the directional derivative is minimum, right?
Yes, sir.
Rate of change of temperature is minimum means along that direction, the derivative should be minimum, right? So directional derivative should be minimum. So basically this is minus of grad. That is the vector we are looking, right? At -1, 2. So what is grad of f? We have already calculated it somewhere. So this is 2xy square plus 2xy, right? Comma 2x square y plus x square, correct? So grad of -1, 2, what is that? Can you find it? What is that? Anyone? I have to calculate it.
-10.
So -8 plus 2 minus
-5.
right?
-4.
-4. And what is this one? 2, 4 plus 1. So -12, 5, right?
Yes, sir. -12.
So along 12, -5, along this vector, this is minimum rate of change of temperature, right? Minus
Yes,
of this vector. And where it is maximum, this is the next question. So along -12, 5, it is maximum. Okay.
So when we are asked the direction, what should we give as the answer?
The vector.
Is it supposed to be the unit vector?
Okay, yeah, good question. No, you can give it just the directional derivative.
Because there
I mean,
was a
just the
question in
gradient vector.
activity question like where the vector and the unit vector both are given, and unit vector was the right answer and the normal vector was.
What was the question?
I didn't remember exactly, but
both are direct to the same direction. Both unit vector as well as the both will be pointing towards same direction.
I think that question asked us to give the unit vector.
Yeah, that should be the case. Otherwise, can you tell me which question was it? This is the question basically I am doing, and here all the options are basically unit vector that is given, right?
Yes, sir.
Yeah. So it depends on the option which, if unit vector is asked, definitely you have to give it.
Sir, can you solve third question, sir?
Activity
Same
question.
thing. Yeah, probably. I'm not sure if my derivative is right, but I think yes, this one.
I was not supposed to take activity question. Okay. So if after this is the function, which are the following? You have to calculate grad f, right?
Yeah, correct. I did calculate it. Okay, so this
which one
this
are you
like
getting?
Actually, what I'm getting.
It should be the third one, right? No?
Yeah. No, sir. Options are like four. Last two options are coming, sir.
The third one is not coming.
No.
Okay, so gradient function. What is the gradient function? Okay.
Yeah, so I did del f, del fx, and del fy. Okay,
so can you tell me what is f?
E की power x square plus xy plus y cube. Yes, sir. This is
So
one.
what is fx?
So it will be like complete e की power complete thing. Yeah, you can do x x then yeah, this one same thing will come over here. Yeah, and fy it will be x plus 2y. Yeah, x plus 2y. 3y, sorry, x plus 3y. Yeah, 3y.
3y square.
Yeah, e की power. Same thing.
Hmm.
Then we'll put 1 1. We'll put 1 1 over here. Fa. Yeah, 1 1 over here. 3, I think it will be 3e cube. Yeah, yeah.
Right?
Yeah.
So what is the question now? So this is not what we are getting? No. No. So third option is not correct. Okay. And increase most rapidly in the direction. Okay, at 1, 1. Right?
So third option is not.
No, third option is not correct.
Yeah, yeah, correct, sir.
Third option is not correct. In this direction.
So solve with us question number 3 in this weekend.
Yeah.
Solve with us assignment question number 3. That was the question I was talking.
Not this one.
No, sir. This is what I have asked.
Okay, okay.
That's some other guy asking the question, sir. That's a different question.
Okay. But there should be some E, you know.
No, sir, it shouldn't be. If we take the unit vector, here it is unit vector has been taken.
Oh, okay.
The
We are
norm
only taking
we take to norm.
We have to divide it with norm, right? So this is the vector grad A. Now norm of grad A.
So square of each term, right? And root square of
So which one is coming? What is coming?
So 1/5 of 3, 4.
I mean, this is not norm. I mean, after dividing with this norm, right? This is the unit vector. Okay.
Now, sir, can you please go to the question number 3 in solve with us?
Okay.
There was a fourth option is correct, and
okay.
Third one is no.
So this is okay.
So here it has been mentioned to take the unit vector. I mean, in the definition itself.
Here what is mentioned along the unit vector. I mean, here it is given as that, right?
Yes, sir, but that need not be the case, right?
That need not be the case, yeah. Okay, but as Sir has taken this as the, I mean, conventional method, and actually if we don't take the unit vector, then will we get this one as the maximum? No, right?
So the direction will be same, right? And the question is
Direction will
about
be same. Yeah, but yeah, to get
it's
the
not a
maximum value, that should be the case. But as Sir has taken this as convention, then we will stick to that. Okay, we will take the unit vector as the convention. Okay, unit vector along the gradient vector. Okay, that will be better because that will give me the maximum value. Okay. the maximum value of the directional derivative.
Sir, could you
Because
please go back to the page where you jot down the steps for finding the directional derivative?
This one.
Okay, sir. I will say a few statements. I want you to confirm it and tell me if I'm wrong. So first we have to check fx a1 a2 and fx fy a1 a2 in case if that exists or not, and if it exists, what is the value, right? Next step, now we have to check whether fx is continuous at a1 a2, right? Basically the limit is equal to the fx value obtained in step 1.
Right.
Okay, sir, that's all, sir.
Yeah.
Thank you, sir.
Yeah. Okay. Yeah, 1 minute. Let me see what this. So yeah, basically in the directional derivative, the definition of directional derivative, we are taking the direction of the unit vector itself, right? Here what we have mentioned, unit vector. That's why it is better to take there also the gradient vector, because we are eventually going to find where this directional derivative is maximum. So it is better to take this u, what we are getting along the direction. So mention that as a unit vector. That will be better, I think. Okay, that's why Sarah has also taken that as a convention, because in the definition of direction derivative, we are only dealing with unit vector. Okay,
Unit
and the
vector
theorem
is
says
unique in one particular direction. Unit
exactly.
vector is, yes.
Exactly. So yeah, so basically that is the case. Okay, so it is better to mention that this gradient along gradient vector. So let me write this is by norm of gradient. Okay.
So basically, sir, when it's an MSQ, we can select as many vectors which satisfy the direction part, and when it is MCQ, then we select
No,
the
no.
unit
So
vector.
we will give you the unit vector. Okay. So when this type of question are asking, it means that we want you to answer in the unit direction, unit vector direction. Okay.
Okay, so because I came to this conclusion because in activity 1 we have a question where we are not following the unit vector. There are two
But
vectors.
okay, but it's better to stick to that convention.
Okay, sir. Okay, sir.
We will not give such ambiguity in answer. Don't worry.
Okay, sir. Okay, sir.
We will mention it clearly. Whenever it is. Okay. But at least you got the concept, right? What we are doing in gradient descent.
Yes,
Right?
sir.
Yes, sir.
Okay. So okay, so let me stop here today. Okay, so till gradient descent we have seen from week 9 itself, and next time we will see the tangent gradient and the remaining part of this week.
So next session will also be taken by you, sir.
No, I think Shubham will take the next session.
Sir,
Yeah.
In discourse forum, sir, I have raised a request to Sivasi. Sir has replied also. The request was like this. The request is like this, rather, that in this term, like me.
Calculus part one.
Correct. One derivative calculus.
Yeah. We are planning a session.
Because as per calendar, sir, on Friday there is a session on week 10, not on calculus. So when we can expect, sir, that any tentative schedule for that? Because in discourse, sir,
we are planning it on, I think, Saturday. No.
He told on Friday.
Friday evening we are planning.
Friday evening.
Yeah. Friday morning there is a session for week 10.
Correct.
Friday evening we are planning a session for calculus.
What time, sir? What time evening?
7 to 9. Will it be okay?
Okay.
Okay. We will send an announcement anyway. So yeah.
Okay, sir. Thank you, sir.
Okay. So I will upload this thing and I will give the link also. Okay. Yeah.
Thank you.
Yeah.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Is it over, guys?